welcome everybody to today's session. And so it's a great honor to introduce Massimo Fornasier, who will give the first talk of this morning. Okay, thank you. So the stage is yours. So you have 50 minutes.
Okay, thank you very much for the introduction. First of all, I would like to thank profusely all the organizers for accommodating some exceptional needs that I had. So I'm very sorry that I cannot be there in person, and that I had the opportunity now to deliver the talk online. So I thank everybody for that. Okay, so this talk is presenting a couple of papers that I've done in collaboration with some other people, in particular Pascal Hyde, Giuseppe Savare, and Giacomo Sodini. And they are focused on two different aspects of a theory. This theory, it's about somehow the definition of smooth functions on metric spaces, metric measure spaces, and in particular, as a metric measure space that we will consider the space of the so-called Wasserstein space, the space of probability measures with the second moment bounded, endowed with the Wasserstein, so-called Wasserstein distance. And in particular, we study some density arguments or density classes for these smooth functions, in particular, these Sobolev smooth functions. And we prove through this density that such spaces are actually Hilbert spaces, so they enjoy somehow a Hilbertian properties. Additionally, thanks to this density of certain algebra functions, which we will call cylindrical functions, we will approach a second task, which is how to bring such an abstract theory to real computability. And so in particular, we will see how can we approximate numerically functions in these Sobolev Wasserstein spaces, and solve even partial differential equations over such spaces. Okay, so that's the content briefly of the talk. And as I said, the scope, it's somehow the final scope is to try to course a route that allows abstract functional analysis on metric measure spaces to become concretely computable. So to the point that you can really solve problems on metric measure spaces using somehow numerical simulations. As examples of such tasks, one could be the problem of numerical approximation of Sobolev smooth functions defined on metric measure spaces. Another problem is maybe solving variational problem over such spaces, in particular the minimization of functionals or the solution of the corresponding Euler-Lagrange equations of functionals on Sobolev smooth functions defined on metric measure spaces. So these are examples of tasks that could be of interest here. As a first, definitely not trivial example of metric measure space that we can consider, as I said, we will focus here on the Wasserstein space. And as an example of, or a typical example of a function that you may like to be able to approximate. You may think about the Wasserstein distance for a given reference measure from which you want to compute the Wasserstein distance. So let me give some words of motivation why it is interesting to bring the theory of matrix measure spaces to computability, why it is worth to do that. Well, as a matter of fact, in the current analysis of the mathematical foundation, for instance, of deep learning, in particular, how neural networks are able to approximate functions. In most of the literature so far, somehow data and input of these functions is made of elements in possibly very high dimensional Euclidean spaces. It's true that somehow in the course of the time, people have been considering also other structures like graphs as inputs, and they designed neural networks that could better somehow represent graphs rather than pure vectors in an Euclidean space. But somehow, so far, much of the theory that we've done from a mathematical point of view is still based on somehow functions on flats. However, somehow it is to expect that the data may be better considered on a natural metric space. For instance, if we think about classifying or making functions of shapes, well, shapes certainly do not enjoy some of a sort of Euclidean geodesics when they are moving, but they are following other types of metrics when they are changing and moving. And therefore, if you want to use a machine that is able to interpret shapes, then it would be better to try to correctly somehow understand the metric structure. So one example would be here to have two letters, the letter J and the letter V. We can, of course, compute the distance between these two letters by using an Euclidean distance. But we can also do the following trick. We can consider each of these two images normalized at to one. So we sum up all the pixels, and we require that the sum of these pixels is equal to 1. And if not, we just normalize it. And then interpret each of these pictures as a density of a probability measure, and then compute, instead of the Euclidean distance, actually the Wasserstein distance, that could be somehow interpreted as the length in some way of the geodesics that connects one letter to the other letter. And as you can see, somehow in this way, it's possible to say that J is not that far from V, and while the Euclidean distance most likely will indicate them extremely different. This is just an example in a simple manner to understand why it is interesting to try to understand how functions understand also the difference of objects when they are on a metric space. At the end of this talk, we will try to answer this intriguing question. Can we connect the theory of matrix measure spaces and their functional analysis with deep learning? We will see that seems very a far point to reach, but at the end of this talk, we will see that we can connect all these things together. We start some preliminaries that introduce a bit the abstract theory of Sobolev spaces over matrix measure spaces. So we start with a metric measure space. So it's a space endowed with a metric and the measure M. For these spaces, it's immediately possible to define Lipschitz functions. So as soon as you have a metric, it's possible to define the class of Lipschitz functions or bounded Lipschitz functions. And for those functions, or for even a generic measurable function, it's possible to define for a function a local Lipschitz constant. What does it mean, local Lipschitz constant? Here is called asymptotic Lipschitz constants. Well, we are checking how the function f is varying around the point x, and we try to take the asymptotic largest behavior, largest oscillation of the function around that point, okay? You change the point, you change also somehow this asymptotic Lipschitz constant, so it is itself a function of the input. However, somehow this constant is telling you how this function would vary in the maximal extent around the point x, but if somehow the point x would be a point that is drawn according to a measure, so that represent, in this point, we can assume to have a certain amount of mass. If you want to understand how the function f is varying with respect to a distribution of points that are given on the space S, then it will be better to integrate this function, this asymptotic Lipschitz constant, over somehow the measure that describe how somehow the input of functions are distributed. This object is called the pre-trigger energy, and it tells us for Lipschitz functions, so everything is now well defined here, how the function itself somehow works. If we want to have a similar representation that capture how the function vary with respect to the measure, also for functions that are not necessarily so smooth, then we can relax the concept of pre-trigger energy by considering the asymptotic behavior of the pre-trigger energy for any approximating sequence of Lipschitz functions to a given, say, function in L2 with respect to that measure. And this energy represent somehow how the function f is actually varying around somehow, so on the support of this measure m, and it's also sensitive to places where the function f have no support. So in those areas, you do not feel at all somehow how the function actually vary. Thanks to this object, this quadratic type of object, we will see that in some cases is actually really quadratic form, not always. It's possible to define a corresponding Sobolev space. So it plays a role in a certain sense of the respect to flats. It plays a role of the L2 norm of the gradients as it may appear in the classical Sobolev spaces. And this allows you to define both the space and the corresponding norm. And it is known that in general, this space, it's a Banach space, although it does not necessarily always enjoy a Hilbertian structure. So we will see that somehow in the case where we are interested in, which is a Wasserstein space. So when S is the space P2 endowed with the Wasserstein metric, somehow this space is actually Hilbertian, but we will see that in a moment. Okay, other questions so far?
I don't think so.
Okay, thank you. Okay, I mentioned the space P2. We call it the Wasserstein space, the space of measures, probability measures with second moment bounded. And we defined on this space the well-known Wasserstein distance, which is given by the cost of transport between one probability measure to the other probability measure. And this cost is quadratic in space. That can be computed as the integral of the distances squared with respect to any transport plane gamma, which is a probability measure with marginals mu and nu respectively. And this cost is somehow the optimal cost that one considers. And this is a well-known concept, which I'm not going to describe more in detail. Maybe it's worth to mention that the Wasserstein space with the Wasserstein distance is a complete metric space, which is compact if the domain is compact. And somehow for any Borel measure that now we place over the space of P2, we call somehow the corresponding metrics, the corresponding metric Sobolev space, the so-called Wasserstein Sobolev space, which follows exactly the construction that we have been seeing here. As you see, this construction starts fundamentally from Lipschitz functions. So basically, one sees that this space, according to results, for instance, by Ambrosio, Gigli, and Savary, enjoys the density of bounded Lipschitz functions in a strong way, and certainly Lipschitz functions are an algebra of functions that can build these spaces by density. However, despite it is not that simple to fabricate interesting Lipschitz functions on the space P2, of course, one of the most obvious Lipschitz functions is the Wasserstein's distance itself. But once you have it in your hands, you realize that even this function is not that simple to compute. There is a huge literature by now of pointwise approximation of the Wasserstein distance. So I give two probability measures, and I want to compute numerically the Wasserstein distance. By now, there is a very broad literature that explore this problem, and we see that somehow algorithms are very efficient by now to do that. However, they don't scale necessarily very well with the dimension of the space K or the domain K, and somehow there is a vast literature to do that, and it's also it is also been considered for a long time a non-trivial problem to be able to compute even pointwise the function W2. We will come back to that later. Now, there are other functions that are much easier to fabricate on Wasserstein Sobolev spaces. In particular, somehow we can construct the so-called cylinder functions. We fix an integer n and a function psi that maps Rn into R, and this function is supposed to be smooth enough and bounded. And at the same time, we fix a vector-valued function that maps the domain into a n-uple of smooth functions, and we call it phi. According to that, we can define a first object that we call maybe first layer, that takes as an input a probability measure and maps it into a vector in Rn by integrating the given measure with respect to the phi1, phi-n functions. And this first layer is then passed in composition to the function psi to form a function f, which is going to be a function on the probability space of probability measures. And this function is right away called a cylinder function. As you can see, this function is quite computable in a sense that as soon as you are able to compute integrals with respect to measures, then you can approximate function phi1, phi-n in some way. You can approximate the function psi in some other way, and altogether, these functions can be approximated numerically somehow. That's a bit the advantage of being able to compute somehow on the space pk by using these functions. For those that are minimally familiar with neural networks, you can see quite immediately that this first layer function, the L phi, maps the input, which is a probability measure, into a vector. And then this vector is passed to another function that may be itself a neural network. So a neural network is nothing else a composition of somehow affine functions with certain nonlinearity, so certain nonlinear functions. And so what you can see is that cylindrical functions themselves are right away prone to be approximated by a neural network right away. So that's so an anticipation of what will come towards the end of this talk. Just for notation, we somehow introduce this notation for indicating the set of cylinder functions that are bounded as smooth. Okay, a first result is the following, that the asymptotic Lipschitz constant that we introduced at the very beginning of the theory of Wasserstein, of metric measure spaces and their Sobolev spaces, the Lipschitz, the asymptotic Lipschitz functions that is input dependent, can be expressed in a explicit form as a quadratic function with respect to an object that we call the Wasserstein gradient of the function f, and the Wasserstein gradient of the function f, for f being a cylindrical function, is explicitly computed in terms of certain gradients and derivatives or directional derivatives of the composing functions. And interestingly enough, somehow we do have this very nice relationship that the square of the asymptotic Lipschitz constant is exactly equal to the L2 norm of this Wasserstein object. As a consequence of this, the pre-trigger energy, which is the L2 norm of the asymptotic Lipschitz constant, can be also explicitly given in this form. Okay, we will come back to that in a second because it's very important. The proof of this proposition is based on the fact that somehow when you try to compute the variations of a cylindrical function along transport solutions with L2 vector fields, say VT, which could be the Wasserstein vector field that realize the Wasserstein distance between two measures, then you can see that somehow the variation between 2 points can be expressed in the integral form where this object df naturally come into the game, and say you can immediately see that the asymptotic Lipschitz constant here by Cauchy-Schwarz can be immediately be bounded by the L2 norm of the Wasserstein gradient F, and therefore somehow actually you can prove also the other way around by using certain optimal paths, and in this way you achieve this identity. Okay, so this is interesting because now we see that there is an algebra of functions, which is this algebra of cylindrical functions, for which a lot of objects that we introduced so far are actually computable, all of them. We are able to compute the asymptotic Lipschitz constant. We are computing the pre-Cheeger energy. So there is a lot of things that we can do with this algebra. And here comes the first important result. We see that there is actually the density of cylindrical functions into the Sobolev Wasserstein space. In particular, for every function f, there exists a sequence of cylindrical functions such that you can approximate strongly f in L2, and the corresponding Cheeger energy can be approximated by the pre-Cheeger energy computed somehow on the corresponding sequence of cylindrical functions. So everything can be approximated by computable objects. The Fn is computable because it's a cylindrical function, and the pre-Cheeger energy is computable because made of derivatives and integrals that may be computed. Another important fact is that the pre-Cheeger energy obviously can be associated to a quadratic form, because we can somehow consider certainly a scalar product here of any Wasserstein gradient against any other Wasserstein gradient, and that form clearly gives as a diagonal the pre-Cheeger energy. So this is a quadratic form that is underlying this density argument that is preserved as soon as we relaxed everything and we allow somehow these limits to take place, which gives rise to the fact that somehow the Cheeger energy is actually itself a quadratic form, and the space, this Wasserstein Sobolev space, turns out to have a Hilbertian structure. And in particular, there exists a natural product or a sort of scalar product here that is generating this function here. So this is perhaps a surprising result in the theory of metric measure spaces. The fact that the Sobolev space is Hilbertian is somehow called infinitesimal Hilbertianity. It's often a property that is assumed. It has been, or it is derived by certain somehow other properties, and it here comes from this density argument through the cylindrical functions. So how this theorem work? So as a matter of fact, functions can be, say, Lipschitz functions can be approximated by a sort of op-flux regularization. So basically, you consider some quadratic distance term that is regularizing the function, and this allows to show that Cheeger energy built from cylindrical functions coincide with the one built from the one built through the density of bounded Lipschitz functions can reduce to show properties of the Wasserstein distance. So you take functions You approximate them by off-flux. In off-flux, there is a distance term. Somehow you represent function in that way. So understanding what happens in terms of the Shiger energy of those functions, it's basically understanding what happens to the Wasserstein distance. And finally, the result follows by the approximability of Wasserstein distance by cylindrical functions by Kantorovich duality. I will get back to this particular element of this theory, or particular building block of this theory, the approximability of the Wasserstein distance by cylindrical functions, because it will be somehow the core of what comes next. So other questions so far?
I don't think so. No.
Okay, thank you. Okay, as I said, let's look at the approximability of Wasserstein distance by cylindrical functions. And we assume now that one of the two measures in the pair is fixed. So we assume that we have a given theta probability measure, and we want to approximate the Wasserstein distance as a function of the only the first entry of it. The main idea is to use Kantorovich duality to construct cylinder functions that approximate it. So for regular somehow measures, so measures that may be absolutely continuous or maybe have a compact support, then it's possible to show that there exists a pair of functions such that the Wasserstein distance between two measures correspond to the integration of those functions against the two corresponding measures, although these functions do depend on the specific measure. So you change the measure, then the function phi star and psi star would change. They also correspond to optimal functions in the sense that there are those functions that are dominated by the square distance and they are smooth enough. And those functions somehow are also the optimal one in the terms of this first supremum. But given the fact that one can consider a dense, a countable dense subset of the probabilities, we can also consider all the corresponding pairs of Kantorovich potentials functions, which are called phi k and psi k, and derive the Wasserstein distance actually as a supremum of all these integrals that we do with respect to these Kantorovich potentials associated to the pairs mu k theta. Okay, so all of a sudden somehow we can see that there is a external function which is the supremum, and there is an affine function again in the interior that resemble right away a cylindrical function. Therefore, through suitable approximations, so taking a finite number of Kantorovich potentials or finite number of elements of this dense sequence, at the same time, by approximating the supremum function by a smooth function and so on, we can construct a sequence of cylindrical functions where the cylindrical function mu n, so eta n, is nothing else than an approximation of the function maximum, the maximum function on n entries. And the V1s are nothing else than suitable Kantorovich potentials of a subset of the mu k's. Then this function converge pointwise monotonically to the Wasserstein distance. So we can always find, in this way, it's possible to construct somehow this nicely. And this tells us already that we can approximate the Wasserstein distance pointwise nicely if we take enough Kantorovich potentials. So we have a guaranteed convergence. The only problem is that we have no idea of how fast, somehow, how many of these Kantorovich potentials we need to take. It might be that we need to take a very, very large number of Kantorovich potentials to approximate well each other evaluation of the Wasserstein distance with respect to a certain measure mu. So there's no real benefit in understanding how well we can approximate here. However, using the same construction, we can produce a probabilistic type of result that won't hold deterministically. So you won't tell us what happens somehow pointwise or for sure. And it works like that. Instead of having a sequence of dense measures, we take a sequence or a certain finite number, actually, of measures that are drawn at random according to a probability measure over the space, over the Wasserstein space. So, which means that instead of using a generic Borel measure M, now we are using a probability measure over P2, and we generate at random these points mu1, mu_n, and we construct in a very similar way a cylindrical function Fn, and one can prove that the L2 distance between these two functions in expectation with respect to the mu1, mu_n drawn at random can be estimated in a quantitative fashion, in the sense that we do have an arbitrary epsilon that we can pick, and with this epsilon we construct certain objects that are called epsilon n subcovering probabilities that tell us what is the probability that a certain measure mu drawn at random with respect to P belong to one of the balls of the other measures of radius epsilon, where the other measures are also drawn at random according to P. And what you can see is that somehow you have this quantitative estimate, and the question is how these subcovering probabilities behave. The good news is that as soon as K is a compact set, the subcovering probabilities converge to 1 with an exponential speed. And this, the rate of this exponential depends on epsilon. For epsilon smaller, become slower, but for any fixed epsilon, you know that for n going to infinity, P epsilon n goes very, very fast to 1. And so you have actually here a very quantitative estimate of error. Okay, this is one way to deal with the Wasserstein distance, but what about other functions? Well, for other functions, we don't have, in general, this Kantorovich representation that somehow bring us quite directly to cylindrical functions. We need to use other tools. And the tool that we want to use is what the people call empirical risk minimization, which is, let's assume that we have a sequence of measures, an empirical sequence of measure that converge to our measure over P2, and that we consider a subset or a suitable subset of cylindrical functions, and we assume that is a finite dimensional subset. And we consider the Jn functional that tries to compute a function in H12, or actually in cylindrical functions again, such that this function evaluated on points is not too far from the given function f evaluated on points. At the same time, we are requiring maybe this function to have a bounded pre-trigger energy by a regularization. And what you can prove is that for suitable choice of the subsets Vn, this functional that was somehow norms are measure dependent because they depends on Mn and n is changing. Thus, obviously, gamma converge to the expected functional that we have here. And in particular, what we have is that we have convergence of minimizers in L2. And if lambda is strictly positive, we have convergence of minimizers in H1. And therefore, somehow this theorem tells us that if we want to approximate the given function f, we may compute over this finite dimensional subset a minimizer of this functional that can be written on a finite number of atoms. So all the integrals here are simply finite sums. So this is a finite dimensional optimization that one can do. However, once again, we have guaranteed convergence, but we do not have a convergence rate. Okay, so as we have done before, instead of using a deterministic argument that may not lead us with a convergence rate, we use a probabilistic argument. So we, instead of having a measure M, we consider a measure P, which is a probability measure over P2. So we assume again K compact, P a probability measure. We consider any finite dimensional subspace of the cylindrical functions, again, finite dimensional subspace. And we consider again an atomic approximation of the measure. So, and with this, we can construct this empirical functional as we have done before. And we can consider the unique minimizer of this convex functional over Vn, and being Vn a finite dimensional subset is actually subspace. And this functional being computable through sums, given the atomic measure, then of course this is a classical optimization that you can implement on a computer. Actually, being a strictly convex optimization, it can be solved by using any suitable orthonormal basis of the space Vn. By using this orthonormal basis, we can transform this quadratic optimization problem into a linear system. And so you can solve it very nicely by using such a linear system. The first result tells you the following. If you have a function f that you want to approximate, and it's a measurable function that is bounded with a bound that is, say, m, then the truncation of the minimizer of this finite dimensional problem, okay, this truncation will enjoy a quantitative estimate of error in L2 over the entire probability measure. And this error is made of three components. A component which is dominated by the trigger energy of the projection onto the space Vn, P P and F, the distance between F and P and F, so how far is F from its projection onto the space Vn, and then a rate of convergence that is quantitative, that depends on the bound M and the constant and the number of points on which we are sampling the function F. Now, here we have to choose capital N sufficiently large with respect to the little n, where little n is the dimension of the subspace. So if you have enough points with respect to this space, then this error will be enjoyed. There is one problem in this theorem, that it's difficult to quantify and to optimize the first term of this error. So you never know what is the optimal subspace that you have to take in the way to make the first term of this error small. And there comes the optimization of a neural network later in this talk. Somehow, a similar result holds when we are dealing with noisy data. In this case, it's a bit more evident the role of the regularization term lambda. Lambda can be used in the way to somehow control the noise. So if you have a large noise, you can control it either by taking more samples or having a more regularization. Although more regularization means that the second term of this error may grow. And so there is a sort of optimal lambda that you have to choose according to n and according to the variance of the noise and so on. So this is just to clarify how the regularization lambda will affect noisy data. As I said, it's not always easy to determine the best approximation space. That's why you can use neural network. And now I come very quickly to the numerical experiments. I just skip the last part. As I said, you can interpret data as somehow probability densities as soon as you normalize them. So if you say transform all these color pictures into gray level and then you normalize them, then you can create somehow the densities, and then you can compute the Wasserstein distance between them. So here we can see what happens with the first approach. So in the first approach that we saw, you can approximate the Wasserstein distance by using Kantorovich potentials and the corresponding cylindrical functions. And you can see that the more potential you take, the more you're able to improve the error that you have on. So if you take a certain number of potentials and you want to check somehow how good is your approximation with respect to the entire database, you can see that if you take 10 to the 3, let's say, or 10 to the 4 potentials, and then you try to check what happens with respect to the entire database, is much larger than that, you can see that you can obtain quite nice approximations already. Now, one aspect is that the maximum function can be implemented as a neural network. I'm not giving the details. I'm telling you that by using very simple operations and by using the so-called ReLU activation function, it's possible to build very easily the maximal function. And therefore, somehow you can implement all these cylindrical functions that I illustrated here actually as neural networks. And as such, you can decide now to train these neural networks by minimizing the corresponding weights and using as cost functionals the empirical risk minimizations that we have done in the second part of the last part of the talk. So if the dot line is the approximation level that you can have of the Wasserstein distance over the entire database by using Kantorovich potentials, you can see that you can improve both for the first database that is called MNIST and the second database that is called CIFAR. You can see that somehow you can train the neural networks. In the first case, you can improve with respect to the Kantorovich potential. A bit surprisingly, with respect to the CIFAR, it's much better to use the Kantorovich potentials as an approximation. Instead, somehow, if you allow a full training of these neural networks, both in the case of the MNIST and in the case of the CIFAR, you can improve with respect to the Kantorovich potential approximation. Let me say something about the computational cost. So, as I mentioned at the beginning, the computation of the Wasserstein distance pointwise, it's a field with a very large amount of contributions. And if you try to approximate for each probability measure and using these algorithms, the Wasserstein distance on a new input, this will cost a certain amount of time. So if you have a database and you want to compute the Wasserstein distance of, say, all the numbers to a given number, and you do it by computing pointwise this all the time, this will cost 10 to the 4 more time than implementing this algorithm that is based on pre-training and then evaluating exclusively somehow this cylindrical function pointwise. If you want to consider even the training of the function itself, then nevertheless you can improve of even 5 times somehow the computation over the entire database. So this is just to show that this theory allows you to break of a several order of magnitude the computational time of the current practice in numerical analysis of Wasserstein metrics.
Massimo, you have just 1 minute.
Yeah, I think that I'm over time, so I did not mention that beside somehow solving the optimizations by training, say, neural networks, minimizing these functionals, you can also try to solve the corresponding Euler-Lagrange equations. So these are really corresponding to sort of elliptic equations over the space, H1, and you can also solve these equations by solving the corresponding somehow saddle point problem or equivalent saddle point problem in terms of a sort of adversarial training of 2 neural networks, one neural network that want to realize the supremum and one neural network that want to realize the infimum. And also this can be implemented numerically, and it's actually giving very, very good results in terms of efficiency and error on this very difficult problem. Okay, so I thank you very much for your attention, and I'm sorry that I went a bit over time.
Okay, so thank you for the very nice talk, interesting. Are there one question?
So, Massimo, thank you for the very nice talk. I have one question, but it's more on the theoretical side of your approach, not on the very nice applications you presented. So you started from a metric measure space, and by means of Lipschitz functions, you somehow approximated the Dirichlet energy, or the Shiger one, the modulus of the gradient. So this is the Sobolev space of order 1. Would it be interesting to approximate Sobolev spaces of order 2, like, for instance, modulus of the Hessian square? Are there some techniques available? Because this one, based on Lipschitz function, is maybe doomed to failure. And can you devise some application where second order differentials in some sense could be of help?
Okay. So what I can say is that as far as I know, there has been some work by Gigli and collaborators that started to think or to a sort of second order type. I don't know the details in the way they proceed in the abstract setting. I don't know whether it's possible simply to replicate somehow the idea that certain concept of gradients could be themselves Lipschitz and somehow reiterate the construction. That's something I don't know in the details. Concerning maybe the application to Wasserstein Sobolev spaces, I think that one can consider higher order differentiation, of course, because if you choose somehow sufficiently smooth functions, you can reiterate a little bit the construction, obtaining somehow certain type of objects here, gradients that are, say, somehow forms that are kind of bilinear or multilinear, or no, not bilinear, multilinear, that are multivarying and obtaining a sort of concepts of Hessians to a certain extent. Whether this will lead to density arguments and the construction of a Hilbertian Sobolev space, that's something I don't know. This is an argument that we were chatting vaguely without getting ever into the details. So I think that there is some work done by Gigli and others, or it's it is on the way. Or about applicability, I don't know. I have no idea. My feeling is that, so if you want to be very speculative on what you can do of interesting, you can do some functional or variational calculus. So as soon as you have gradients, square gradients, you have Sobolev spaces, you can write right away, for instance, a Manford-Shah problem in the sense of Ambrosio and Tortorelli, so in the sense of the approximation. And this brings you to the problem of understanding whether you can construct a sort of BV spaces or special BV spaces. And there are construction of BV spaces on mesometric spaces. I don't know whether there is any progress in having done anything about sort of special BV spaces. But you can see that I don't know whether going into the second order is very complicated and useful, or is but there is plenty of things to be done already at this level somehow.
Thank you.
Okay, so we thanks the speaker again for his nice talk. And the second speaker of this morning is Professor Totzeck, Claudia. And she will speak about on the port-Hamiltonian structure of interacting particle system. Please.
Very much, Giacomo, and thank you. It's on, but closer. Okay, now, yeah. Okay, so thank you very much for the introduction, and to all the organizers for the invitation. I really enjoy being in Italy again. And before I start, I want to say it's joint work with Birgit Jakob, also from the Bergische Universität in Wuppertal in Germany. So I think that some of you are not familiar with port-Hamiltonian structure. So a huge part, or the first part of my talk is kind of introducing the structure, give you some historical remarks, and then we want to link the structure to interacting particle systems. So basically, we go to all the ingredients and how they are coupled and so on. And then the next part is kind of connecting and using the structure and to show long-term behavior of the systems. So I think you might see some relations to the first talk of yesterday, which was very nice. And now we pick up the system. It's a little bit different, but we will see in a second. So starting with historical remarks here, I take a very well-known toy problem, so the mathematical description of mechanical systems, and we start with Newton. So in the 1680s, he proposed to use a particle-based approach and to describe the mechanical systems using position and velocity in Cartesian coordinate system. So basically, we all know, so force is driving the system. We have here the mass, which will be set to 1 for the rest of the talk. And then to have it well posed, we need some initial conditions, both for the position and the velocity, because it's a second order system. Okay, equivalently, we can put it like that as a first order system, but then with basically 2 entries. And what was new at the time was that it unifies the framework for celestial and terrestrial physics. So you can describe when you throw a ball up to the movement of planets by just one set of equations, which is of course very impressive. Then about 100 years later, there was Lagrange, and he has a very mathematician approach. So he said, let's generalize. So first he generalized the coordinates. So it's just Q, and Q can be more or less anything. And he chose a description in the configuration space. So you have Q and Q dot, which if you relate it to the slide before would be position and velocity. And instead of describing the initial conditions for both these vectors, he specifies the initial state and the terminal state. And then what I like as an optimizer is that you can relate the approach of Lagrange and the one we've seen before by Newton by an optimization problem. Of course, you need to choose the correct cost function. So the Lagrangian is set up by the kinetic energy minus the potential energy. And then the principle of least action connects the 2 principles by the Euler-Lagrange equation. So they are equal to the Newton's equation. So this is, of course, a link between variation calculus and optimization and the Newton's second law. So then we move a bit forward in time, so 50 years, more or less, and then Hamilton was around, and he said there should be some geometric structure behind all this. So the Lagrangian is nice, but there should be more geometry. And then he played around and proposed to use the momentum instead of velocity. Then this leads to a phase space of these 2 guys in conjugate variables. And you have the Hamiltonian, which is the Legendre transform of the Lagrangian. And now you sum up the 2 energies. So you have, again, the kinetic energy and the potential energy. And basically what is changed is the minus sign, to say it very rough. And the geometry behind is now the Hamiltonian equations. So if you split the systems and look at the ODEs for Q and for P, then you have here the 2 derivatives and the minus. And we rewrite this now, and then we see here this symplectic structure. So it's a skew-symmetric matrix multiplying basically the gradient of the Hamiltonian. And you see that by direct computation, you have energy conservation. So nice. So now we have a link from geometry to optimization to Newton. Yeah, so that's quite strong. And now we go one step further. So now we want to go to port-Hamiltonian. So, and how to do that? Up to now, everything was closed. We set ourselves in the ideal perspective that we have a closed system and the energy is conserved. So in reality, energy is usually not conserved, and we want to connect pieces, because to describe the whole picture, sometimes it's good if you have just the components and you know how the components interact. And this is what the ports allow us. So the focus is on coupling. And one other thing is that you can also account for energy dissipation. So also here, there is a geometric description, and it's basically all hidden in this Dirac structure. So you have the energy storage element, the Hamiltonian. You have a dissipative element where you can lose energy, and you have external ports. And these external ports, you can interpret them as control ports or external ports for coupling. And these allow to plug together systems. And we will see that if you do this in a port-Hamiltonian correct way, then you again have a port-Hamiltonian system. So some background on this Dirac structure. So if you have a linear space V and the dual V star, then the elements of V are called flows, and the elements of V star are efforts. And then a constant Dirac structure is a subspace that satisfies this relationship. And in particular, what is important is that it's power conserving relation. So you interact with the external through the ports, and if you do it in a correct way, then the power you give is taken from the other system and back. So then overall, it's again power conserving, but if you take one piece out of the puzzle, it may be dissipative. And then this vector E and F are usually in this picture consist of three parts. So you have the storage element, the flow and the effort, the resistive element, FR and ER, and then the external ports for coupling and interaction. Okay, that's this. Let's move to some equations. So with the simplest ODE port-Hamiltonian structure reads like that. So you have the state Z, which you can think of consisting of positions and velocities. And then you have here two matrices, the J, which is skew symmetric, maybe this one, and the R, this is the resistive part. So it should be positive semi-definite. These two guys multiply the gradient of the Hamiltonian, and then you can have inputs that are usually smaller of dimension-wise than the internal state. So B is a matrix that maps the small input into the system. And then you have the output, Y, which is given with this structure. So once you have the input and you solve this, you can get the output directly by this small computation. What happens here is because of the R and the skew symmetry, you get the dissipation inequality. So if you do the same computation as you would do for a Hamiltonian system for conservation, you see that the skew symmetric part cancels out. And then what you're left with is here this positive semi-definite part with a minus sign. So basically you have this, and using the definition of how the input enters and the output, you can even rewrite it. And then you can see that over time, the Hamiltonian, so the energy of the system changes only with respect to the output and the input. So that's what you expect, right? You give something or you take something, and this is what the thing changes. If you forget about U, you said U equals to 0, then you have, again, conservation. Okay, so now you might say, okay, I've seen something similar, and I talked to several people like Oliver about this structure, and he said, oh, it seems to be close to generic, and other people told me like, oh, it's also some relation to metriplectic structures. So I want to put them in this picture. So Morrison proposed the metriplectic systems, and these look like that. So you have a dynamical model of thermodynamics. So you want to kind of satisfy the first law, the conservation of energy, which is of course also happening here, and the second law of entropy production. And then you define the free energy as the sum of the Hamiltonian and entropy, and you get this kind of structure. And here, of course, the Hamiltonian is also there, but what is not there in the port-Hamiltonian structure is the entropy. So this is a huge difference. And also, here are no ports. So the ports are the most important thing in the port-Hamiltonian system, and these are connected to closed systems. Yeah? So this is kind of the thing. Port-Hamiltonian systems are in general open, and they focus on coupling, and they have no entropy. So this is kind of setting the concepts into relation. Okay, so now I spoke about these connections and the port-Hamiltonian way of connecting things. And this is basically to be power conserving. So let's do this for two port-Hamiltonian systems and see what happens. So basically, we have now two, I is 1 and I is 2, and they have the same structure. And now we interconnect in such a way that we said U1 to Y2 and U2 minus Y1. So the minus is important. And then the two equations that are here, we rewrite them in this vectorized form. And then playing a little bit with the equations, we get this. And we see here again the structure. So we have our skew-symmetric J and the skew-symmetric J2. And here, this is skew-symmetric 2. So this is preserved. Here we have the two dissipative parts, but only on the diagonal. So this is fine as well. We have here the two gradient of the Hamiltonians and so on. So we can basically give it a new name, and it's again a port-Hamiltonian structure. And this is what makes it so nice, yeah? That you can couple them in a power-conserving way, and then you can plug systems together and still have the structure. So this also works in infinite dimensions. So here we have the variational derivative. Here with the operator, we have to be a bit more careful because of the possibly different domains. So we cannot, in general, write J and R as we can split in finite dimensions. But this should, of course, still be dissipative, and we have then this relation where here these brackets are the inner product of a Hilbert space, for example. Okay, this is the concept that we now want to use and apply to interacting particle systems. And to start into the thing, let's have a short movie. Maybe you can see here the relation to yesterday. So interacting particle systems, when I think about it, it's most of the time kind of biological things, like here this flock of birds or the fish we have seen before. And since my PhD thesis, of course, also the sheep and the dogs, which are not present in this movie. And here we also see alignment. Yeah? So this will be on the next slide, very important. So now let's do this mathematically. Alignment would mean you have a flock, and over time, the velocities, which are represented by these arrows, align in the same direction. So now the flock travels. And then we can also do repulsion attraction kind of dynamics. So we put the flock together, and we have these Morse potentials that we have seen yesterday too. And then here some friction is added, but the message is that the flock spreads until everyone has the comfortable zone, and there they stay. And if you write these equations down, then it looks like this. So you have again kind of a Newtonian structure, and you have two interaction terms. So here's the alignment. In this talk, I will use the Cooker's-Mail version. And we have here the potential, so the gradient of the potential for the other interactions. And what is already good to observe that we have these sums. So kind of every particle has the same influence weighted by these function values somehow, but everyone is interacting with everyone. All right, so how is this related to the port-Hamiltonian structure? Or first, let's some details. So we assume that the phi is only a function from R to R strictly greater than 0. And you can see here why we can do that. So we put the absolute value, so the distance of two particles inside. So this is kind of just evaluated at R, and it maps to strictly positive. That will be important. And we can see here that also the difference of the velocities plays a role. And altogether, if we look at one particle, then the force is kind of a superposition of the binary interactions. That was also mentioned yesterday, but only for this term, and this term looked a little bit different. Okay. Yeah, so now how is this related to the port-Hamiltonian systems? So you can interpret this as a spring mass damper system. So each particle is the point where the mass is located. And then you have either the spring, the generalized spring for the potential interaction, and the damper is the alignment term. So then you have Hamiltonians of the subsystems. So for the mass, it's not so interesting. It's just the kinetic energy of the mass. Then for the spring, you have the potential energy of the spring, and for the other mass, you have, again, the kinetic energy of the mass. The damper is purely dissipative, so there's no Hamiltonian related to this, but of course it will still pop up in the location of the R matrix that we have seen before. All right, so let's describe first the subsystems as port-Hamiltonian systems, and then we couple them and we see what happens. So one piece of mass traveling through space has a position and a velocity. The kinetic energy is this one. And then we have these forces, so the flow and efforts, that is important for the coupling of the port-Hamiltonian systems. And we can write them down as F is just the input, basically, and the effort is what we get out, is the velocity. Then if we plug this in, we have this dynamic as Newton equations. And if we do the same thing of stacking the x and the v together, we get this z variable. We can write this like that. And we have here the skew symmetric part. There's no damping or anything here. The mass is just traveling. So it's we have the input, the force, and then, yeah, this is the dynamics. How is it for the spring damper? So for the spring damper, the first observation is that everything is relative. So we move to relative positions, Qij, which is the difference of the two masses. And we have also relative velocity, so Vij, also relative. And then we have the potential energy, which is the potential that we assume, and the damping. So then, of course, also here we can put external forces, and we get the effort directly from the output equation. So writing everything down in this system, we get this equation. So here we have the Hamiltonian for the spring damper, which is just the V, but the derivative, so as we've seen before. And then we have here this damping prefactor times the difference of the two velocities. Rewriting in the port-Hamiltonian structure gives us this one. Again, here the skew symmetric part, then here the damping part, and how the input enters the system is given like that, and the output can be written like that. All right, so now we have efforts for both systems. I mean, for the mass J, it's just the same. So we can plug the things together in a power-conserving way. And once we do that, we obtain the following. So we want to couple the mass I and the mass J with the spring damper Ij. So we have the two masses, and in between the spring damper. And then defining the force I, we said minus Eij, as it was proposed by the coupling of the two port-Hamiltonian systems. We obtain this. And because the force is antisymmetric and this guy is kind of a symmetric function, we obtain for the other one exactly the same with a different sign. And this is exactly what tells you Newton's third law. Action is reaction, right? So you can see it directly from the structure here too. So for two particle systems, when you plug everything together, we have the following. So the mass I obtains this force from the particle J. And the particle J has here with the different signs exactly the reaction. The Hamiltonian for these two particles is just the sum of the Hamiltonians. So we have here the two kinetic terms and then here the two potential terms. So now we can do this for n. And what we end up with is the sum over n, here and here. And the Hamiltonian is also the sum over the other, so over the sub-Hamiltonians. So nice. And now we can rewrite using the Hamiltonian and the derivative given like this, our system in port-Hamiltonian structure. So now we see the port-Hamiltonian structure in our interacting particle system. And here, this is the damping matrix. It's more or less, if you sum up over one row, you just get exactly 0. And yeah, because this hits kind of the V1, this hits V2, you get this different structure that we have seen in the dynamic. What is important is that this sum over one row gives you 0. This we will use later on. Okay, some remarks on the literature. We are certainly not the first ones interacting with this problem, right? So there's a nice book on alignment dynamics in Birkhäuser. Then there's a lot of work or one article on Hamiltonian anticipation. Also investigating the asymptotic flocking by Kao et al. Then there's a huge literature only on the dissipation. And here I picked one article which is incredibly often cited by Carrillo et al. So here they also consider the Cook-Smale, but without potential. And the idea basically is tracking the support, and the support does not grow because there's no potential interaction. The alignment just puts the support together. And for Hamiltonian, purely Hamiltonian systems, there's of course also a huge literature. And yeah, so what I want to say is with this slide that we are certainly not the first ones studying this problem, but we are exploiting the structure. So we want to relate the port-Hamiltonian structure with these kind of things. All right, so I showed you one description of port-Hamiltonian systems, but actually there's at least one more, and certainly there are lots more. But what was the aim of this alternative is to account for the space invariance of the system. So basically, if you have your flock and you shift your flock 10 meters and you start your interaction, the behavior should be exactly the same as if you started in the other place. And to account for this, you can basically introduce reference points, the center of mass and the mean velocity of your swarm. And what first thing to note is due to the symmetry assumptions on the psi and the v, we obtain that if we sum up over all the derivatives of the velocities, we get 0. That means the mean velocity is conserved for all times. So if we define this v bar, it's invariant. So I will sometimes write v bar 0 or just v bar because it's the same for all times for the system that we study. And then we can introduce the shifted port-Hamiltonian system. So basically, we always shift it with the center of mass, and we end up with new variables Ri. And because we shifted, then also here we have the shift in the velocity. But since the derivative of this guy is 0, we don't see it basically here. So for the velocity, we still have the same equation as before. You can just accept it like that, or you can think of it like considering everything is in a reference frame, and the reference frame is traveling over time with the fixed velocity to get back to the original formulation. Okay, and also here we find a port-Hamiltonian formulation. So we define this. So 1 times v bar is kind of stacking the v bar n times together such that we can take this difference. And then we can see that the v bar is popping up in the Hamiltonian. And the other structure is just the same. So since it's here, it's also here in the derivative, but the I looks the same, the R looks the same. So it's just exactly the same formulation, but just shifted, and the shift is accounted for here in the Hamiltonian. Okay, I made rather strong assumptions on the potentials. I know that there's a lot of literature that generalizes this, but my point here is the structure, not the deep theory on the ODEs. So since I do these strong assumptions, I can use just standard theory to get existence of the ODE solution, and the port-Hamiltonian structure gives me the dissipativity directly. So over time, the skew symmetric part vanishes, and here I have the dissipative part. So I know that over time my Hamiltonian will decrease or stay where it is. And now, exploiting the structure of the shifted port-Hamiltonian systems, we want to prove a long-time behavior theorem. And it's based on LaSalle invariance principle. And because we shift it, we have the advantage that we can show compactness. So if you think about the flock, and the flock is traveling in time, and you consider the x variable, so the position, because the flock is traveling at constant speed at some point, and or all the time, then you will not have the positions in a compact set for t to infinity. Yeah? But by choosing this reformulation and considering the center of mass as well, it's possible to show that this happens. So just to recall, we need to apply LaSalle invariance principle in metric spaces, so both for the ODE and later for the PDE case, that we have a continuous and decreasing function, which will be our Hamiltonian by construction. And we have to show that the orbit is relatively compact with closure contained in some D, which is a subset of our metric space. Okay, so first, let's go to the ODE case. So first we need to kind of characterize our invariant set. And then we want to show the convergence. So what's the invariant set here? Maybe I put the mouse a little bit to the side. So basically, it's like that. So we have this n, we have our solutions, which are these relative positions and v, and this should be 0. And when I start with a solution in this set n, then I know that the function v is constant over time, as we expect. No, not as we expect. So we expect that over time we have the alignment towards v bar. So if I start already in the set, my function, all my velocities are directly positioned at this v bar, and this term is 0. And the proof is very simple. So we exploit that we have the positivity of the psi. And since the psi here is basically contained in all the entries here, we directly have that if this condition is fulfilled, all the VIs must be the same as the VJs. Okay, then we have the time invariance of V bar. So that tells us if we have this one, then we know exactly the value, and it's 1 over n. So it's just the average of the velocities from the initial beginning. Yeah? So this information we plug into our second equation for the dynamics, and then we know, okay, if this guy is constant when we are starting in n, then I have that the derivative is 0. Then I look at the derivative, the explicit formulation. I know that this guy is 0 because these guys are the same. So here we have a 0, it cancels, and then this gives me directly that this term here is 0 too. So this is now the invariant set. And now we want to use LaSalle principle to show that for t to infinity, we converge towards the set. We do again our strong assumptions, as I said, and we exploit that the Vx is strongly greater than 0. And we assume that the gradient of V is bounded, which is usually the case for these interacting particle systems, at least if you are able to apply the strong regularity that we used. So then for every initial condition, we have that the corresponding solution really converges towards the set, which means basically the velocities are really aligning because this is the condition that we have in the definition of the set. And here it is again, so that the VI's are constant and this term is vanishing. So recall for Laplace invariance principle, we need this decreasing function along trajectories. So this we directly have from the Hamiltonian. And then we need that the orbit is contained in a compact set. And here we use a Cronval argument first to get an estimate on this term. And then we use this term and plug it into the R, and we see that this integral here is converging. So we have really a compact set where the full trajectory is contained, and such that we are able to apply Lassalle's invariance principle and have the result for the ODE level. Okay, one example is, as I mentioned, Cook-Smale. So here we have this function psi, which is strictly positive. And due to my strong assumptions on the potential, I use the regularized version of the Morse potential, so here with the squares. And then we have all the things that we needed, and we are fine. So as I said, the Carrillo et al. Considered the dynamics with potential equals to 0 and tracked the support. Then Caro et al. Are also exploiting energy, but not this shifted formulation. And then we have the problem that x goes to infinity because the flocking just drives the positions towards infinity as time goes to infinity. Okay, now the many particle limit. Of course, the first question is now, is the port-Hamiltonian structure conserved when we pass from n to infinity? And we do the standard approach. So we use the empirical measure now with here the shifted system, and we get then this ODE. We have here the differences as we expect, and this allows us to write it here as this convolution. Then for n to infinity, we need to rescale it by 1 over n such that our terms do not explode. But then we get exactly what we expect. So we have here again the shifted kinetic part as we introduced for the ODE case. We have here the potential, and we can write it again as this convolution. So this is just a Hamiltonian. Now, of course, we have to check that we have dissipativity and that we can rewrite the system using the gradient of the Hamiltonian. So the dissipativity I will not discuss in detail because it's really the same thing as for the ODE system. And to check what is the derivative of the H, we do the standard approach using the push forward. So we push our system forward a little bit by some field psi multiplied by epsilon. And then we see what happens in the limit epsilon to 0 when we look at this difference. So we consider this. Then using again the antisymmetry of the gradient of the potential and Fubini to shift around some integrals, we have this expression. So dividing by epsilon and sending to 0, we obtain by rewriting this in a vectorized form exactly this. So we can identify the gradient of the Hamiltonian with respect to the measure f as this guy. Then putting things together, we obtain the evolution of f is driven by this term. So we have here the convolution of f with a times this guy times f. And here we see again kind of a skew symmetric part and the dissipation part that we expect also from the ODE dynamics. So it really translates to the other case, and the port-Hamiltonian structure is preserved. So now, of course, we want to ask ourselves, does the long-term behavior also hold? Here, of course, the compactness is a bit more difficult. So let's see. So we have well-posedness under our strong assumptions in the paper by Canicio and Carrillo and others. And then basically the theorem here is copy-paste from the ODE case. So by our port-Hamiltonian structure, we directly have the dissipation. So this holds. And if we average over all the velocities, then we get our v hat, or which was before v bar, the mean velocity that is conserved. Then our characterization of the invariant set, also this looks quite the same. So we have here our condition again, v minus v bar times the psi, which is depending on the differences, times the v minus v bar, and then here integrated. And starting with some measure in n, we obtain that the two conditions hold, so that the velocity, with respect to velocity, the measure is concentrated at the v hat, and there exists some space-dependent part g such that this holds. So the integral is basically the sum we had before, and I wrote this concentration of the velocities using this Dirac measure here. Also here, everything is very analogous to the finite dimensional case. So let's go now to the LaSalle invariance principle on the mean field. Yeah, we need one more assumption here, that there exists a phi bar below that is strictly away from 0. So in the ODE case, we just had that this guy is greater or equal 0. Here we need strictly bounded away from 0. And then basically we get the same result. So in the limit t to infinity, our measure approaches the set L, and the set L is what we just discussed. So what's the idea of the proof? Of course, we need to work a little bit for the pre-compactness, and then we want to employ again LaSalle invariance principle. So the pre-compactness or compactness in W2, we found this nice result in the book by Pantaretos and Semel. So if we have a relatively compact ZK in P2 that has compact closure in W2, if and only if this condition holds. And recall what we did for the ODE case. We basically said that our trajectories are contained in a compact set. So because of the relationship through the characteristics, if you start compactly supported, you can directly translate using characteristics this also to the infinite dimensional case. That means basically that you can do the same computation, use a Cronval argument, and have that Ft is compactly supported for all times. Of course, here again, you use the strong assumptions that we make. And since this is compactly supported, we can employ this theorem, because basically sending R to infinity, at some time, the ball will be outside of the compact support of our solution. So this will certainly tend to 0. And then we have, using this result, the compact closure of the family of our measures over time. And that means compactness is okay. And for the function that is decreasing along trajectories, we can again use the Hamiltonian. So we are happy here. And we can use this for LaSalle's principle and stick things together and also get the same result on the infinite dimensional case. So that's it. I think I saved some time. So what's the summary? I introduced you to the port-Hamiltonian structure. I think because of this flexibility of looking into several parts, disconnecting them, studying them, and then connecting them in a good way is really interesting also for other topics. Originally, they come from electric circuits. So port-Hamiltonian systems is in the engineering community well known. They study and work with them a lot, and they also use these Dirac structures to build systems and things together. And now the structure is kind of, yeah, also entering in different applications and interesting things. So then we have seen that the structure is preserved when we send n to infinity, and using the structure, we can use LaSalle principle to study the long-term behavior. A short outlook. So the plan is to introduce control ports. So probably you noticed once we coupled all our subsystems, we had a closed system. But of course, you can introduce to the closed system, again, ports, and use these ports to do some control action and then steer the systems, yeah, hopefully in a nice way. Yeah, that's it. I thank you for the attention. And here's the main reference. I'm happy to point you to other references when you're interested. Thanks.
So we have time for questions. Are there any questions by the audience? Yeah.
Yes. Speaking of Hamiltonian structures, I would expect in some limiting cases that you have synchronization of the system. Did you observe that sometimes?
Synchronization, you mean kind of in a Kuramoto model?
Yes, these kind of things, for example, where I mean, everybody works in the same way.
Yeah, so I mean, here now we focused on these structures where we had all these differences. Let's go. Maybe the very here. So we have these kind of things. In Kuramoto, you would have here only the VI, basically. So you set this guy to 1, you get rid of this. So then kind of you don't have exactly the same structure. And also after the talk yesterday, I thought if one could use this self-propulsion term in this framework, it's not straightforward because we really exploit this difference here. But maybe you can massage the terms a little bit and make some assumption like that if you start initially with the sum of all the velocities equal to 0, then you get, if you sum up here again and you don't have the difference, also a 0. And I think that a lot of the stuff relates. But that would be, in the talk yesterday, 2 particles that move exactly on the other side of the diameter of a circle. And so I think there's another assumption here. So in some way, flocking and synchronization is similar, but I think it does not translate immediately here. It's a little more work.
Okay. Are there other questions? Okay, maybe one by myself. So you were speaking about applications in the electric systems. Can you explain a bit more about this? So,
okay, yeah.
Or if you have any other idea of how to apply this framework.
Yeah, so originally, really, it came from circuit systems. So the Bernard Maschke and Arjan van der Graft who introduced it. So Bernard Maschke was expert in bond graphs, and then they met up and said, okay, these connections should have some structure. And then, for example, yeah, if you look at electric circuits, of course, it looks different than here, but nevertheless, you have some resistive part and you have conservation parts. And then the coupling is more or less done in this way, but of course, the flows and efforts look different. But yeah.
So if there are no other questions, so I would thank Claudia again for the nice talk.
Thank you.
The next speaker of today is Chiara Segala from Aachen University. So she will speak about kernel-based learning methods for interacting particle systems in mean field limits. So the stage is yours.
Thank you, Giacomo, for the presentation. And thank you also to all the organizers for giving me the opportunity to present my work during this very nice workshop. So first of all, I present myself. I am Chiara Segala, and I'm currently a postdoc in the research group of Professor Michael Hertie at the RWTH Aachen University. And today I'm going to show you a work that is jointly with Christian Fiedler, Michael Hertie, Michael Rom, and Sebastian Trimpe, that are all from the RWTH Aachen University. And it is a work about a particular type of learning method, that is the kernel method, in the framework of multi-agent system. So first, from a microscopic point of view, and then a mesoscopic. I will compute the mean field limit, and I will go to a mesoscopic point of view. So briefly, I show you the agenda for today. So I will start with a little bit of motivation, even if you had already introductions to this topic from previous talks. Then I will explain what is a kernel-based method and why it can be useful for multi-agent systems. I will then pass, as I said, to a mesoscopic point of view, computing the mean field limit. And then I will show numerical evidence of the theoretical result with some numerical experiments and applications. I will, of course, conclude with some conclusions and perspective for the future. So let's start with the motivation part. So we have that in the recent years, there has been an increasing interest in the study of multi-agent system from different perspective, a multi-scale modeling perspective. Also because we can find a lot of examples in many fields, as you say, as you saw already in previous talks. So we have a lot of application. For example, traffic management, the study of the behavior of very large group of animals, or also a very current topic that is opinion dynamics. If you want to force somehow opinion during the political election in social networks and so on. So as I said, we can study multi-agent system from different point of view. Microscopic, when we look to every agent with its position, velocity, acceleration, we can change the level of description, compute the mean field limit, for example, and have the mesoscopic level that is, instead of looking to every particle, you look to the evolution of the density distribution of particles. And what we can do also, macroscopic level, that is when you study the evolution of the moments. For example, the mean, the variance of your density distribution. So usually what we do with multi-agent system, so in a lot of application, we can apply first principles in order to model multi-agent system. You can think about gas dynamics, for example, when you somehow know how to mathematically write the interaction between the particles. But this is not doable in all contexts. In some contexts, you don't know how to model this system. Let's think, for example, to opinion dynamics. So it's not trivial to understand how to describe mathematically how the opinion between two people interacts between each other. I don't know, you have, for example, study on the overall happiness of a society or the aggression potential of a society. So this is something that you cannot, we don't have principle for that. So what we can do using learning method, instead of model a multi-agent system, we can learn it. We can learn, for example, the interaction of between the particles, or some features of the system, and so on, when we don't know how to model it. And so we have a lot of learning techniques. One of them that is very powerful, it is the kernel method. It is powerful because it comes already with a lot of efficient algorithms, and also it can rely on a very strong theory. So it's basically the theory of Hilbert spaces that I will show you later. It is related to that. And in this work, I will consider this kernel method in a framework of multi-agent system in the case of first many inputs from a microscopic point of view, and then I will consider the limit of infinitely many inputs. So in these slides and in the previous one, I put some references. Of course, there are much more in the literature. And okay, so that's it for the motivation. Now I will show you what is actually a kernel method in the framework of multi-agent system. Okay, so let's consider a very general first order multi-agent system where xi is the state of the particle I, m is the number of particles or agents, and then we have this general kernel that describes the interaction of two agents. So this is called kernel, but keep attention that it is not the kernel of the kernel method. So this is just is unrelated and is the kernel to describe the interaction of two agents. So usually the state of an agent is in RD, and we can consider, of course, the vector with all the agents. And in learning method for multi-agent system, usually what is learned in the literature, a lot of works are about learning the interaction between the particles. What we do here is something different. We want to learn a property of such a dynamics, and a property that is defined on the state space of the multi-agent system. So a trivial example in order to test the theoretical results can be the learning of the mean or the variance of your multi-agent system, because the input is the state, and then you can find the mean of the variance, of course, and the variance. Of course, this is trivial because once that you have the state, it is easy to compute the variance and the mean. But as I said before, you can consider more complicated function or even function that you don't know how to compute. So coming back to the example of opinion dynamics, the aggression potential or happiness of a society and something like that, that can depend on the state. But also you can think about examples where here we have the state space of the system, also for very large group of animals, maybe is not it's not easy, but also not impossible to track the position of these animals, maybe with some video recordings or snapshots. But at the same point, it's not easy to find some features that are related to the state. I don't know, for example, how the group of animals react to an external predator, for example. So this is our what we are interested to do: learn a property of the dynamics defined on the state space. It is important that is defined on the state space also because what we want to do after is to compute the mean field limit, and the mean field limit will be computed in the number of particles m. Okay, so let's see how it works, the method. So imagine that you have your function that you want to learn. Of course, it's not easy to learn, so you need some measurements of the function, and that can be potentially noisy. So you have your function, some noise, and an output. In n points, so you have only n measurements. M is the number of particles and the number of measurements. And these measurements can be, for example, the time frame. So imagine you know the variance at some time step and you want to learn the variance in all the time steps. So this is now just an input-output problem. I mean, you have the input, that is the state, the output in some points, and then you can have a loss function, minimize that, and in the particular case of kernel method, it is proved that the approximation of this function f is given by this formula here, that is a weighted sum of a partial evaluation of a kernel. I will show you soon what is a kernel. And so once you have this approximation in the inference point, your unknown are the coefficients alpha. You find the coefficient, and then you can learn the function in all the other points of your time frame. And the set of the function given by this series forms a reproducing kernel Hilbert space. Now I will show you what it means. And so a little bit of definition. So what is a kernel? So if we consider X an arbitrary set and then H an Hilbert space of functions that goes from X to R, then a bivariate function K is a kernel if there exists an Hilbert space that we call feature space, and a map that goes from the set to the Hilbert space that is called feature map, such that if you take two elements of the set and you apply the map phi, and you compute then the inner product, okay, this is like to evaluate the kernel in the two starting point. So this is the definition of a kernel. Then the Hilbert space H is called a reproducing kernel Hilbert space if the evaluation function is continuous, and in the end, the kernel is called reproducing kernel for H if the partial evaluation of the kernel belongs to the Hilbert space, and if the inner product between the function and the partial evaluation of the kernel is like to evaluate the function. So this just to give you some definition and to understand a little bit what is this kernel that we are using. Okay, so this is the description of a kernel method from a microscopic point of view. What we want to do now is computing the mean field limit. So when you talk about multi-agent system and mean field limit, usually you think to the mean field limit of the particles, of course. Here, we need to compute the mean field limit of a function and of a new object, that is the kernel. So, why we want to do that? Because in many applications, the number of input data, the number of agents can be really large. If you think, for example, a group of animals, but even more with microorganisms, and again, more with gases. When you deal with such a problem, we have a set of n ordinary differential equations, and these can be very expensive, can be also not doable sometimes, especially from a numerical point of view. So the idea is that instead of looking to every particle, you look to the density distribution of particle, and in such a way, you have only one partial differential equation for the description of the density distribution. So now what happened? Instead of the group of particles, you have a density distribution of particles. The functional that we want to learn now is a functional that describes a feature of your system, a feature of this density distribution. And so the idea is that this function, this function is not defined anymore in the state space of the multi-agent system, but, but it is defined on the set of probability distributions over X. And so now, what happened to our learning problem when we don't have agents, but we have densities? So the idea is the same. So you collect some potentially noisy measurements of the functional. And in this case, of course, here we don't have the multi-agent state space of the multi-agent system, but we have the density. We can think again about these snapshots as taken in some times of your framework, of your time frame. And we can use the kernel method again. So this is again an input-output problem. You can apply your favorite learning method. If we apply kernel method, we have an approximation of our function that is given again by this weighted sum, and the input of the kernel here is a density. So now the kernel, the new kernel, before it was defined from the state space of the microscopic, the multi-agent system. Now it is defined on the set of probability distributions. And okay, so there are kernels like this in the literature, but what we want to do now is we want to derive this kernel from the microscopic problem. So we start from the microscopic, we compute the mean field limit, and we want to see what we have in the end, and if this is again a kernel and some features. So regarding the multi-agent system, we said we send n to plus infinity and we end up with a partial differential equation. Now we want to see what is the new learning problem, and this means that we want to compute the mean field limit of this sequence of function where the number of agents is increasing, and and also we want to compute the mean field limit of this new object that is a kernel, and to see what we have in the end. So here it is just the general idea of what happened when we compute the mean field limit of this kernel. And so a little bit of notation. So we consider X with a compact metric space. And then if you consider the set of probability measures over X and the Wasserstein distance, this is proven to be, again, a compact space. And then in order to relate the microscopic and the mesoscopic point of view, you take an element of the microscopic system, you compute the empirical measure in this way, so just evaluated along the state of the microscopic system. We know that this is dense in the set of the probability measure. And then the idea is to consider a sequence of function with increasing number of agents, send the number of agents to plus infinity, and then this sequence of empirical density distribution is supposed to converge to a fixed density probability distribution. So in order to go from this to the mean field limit of kernel, what we do is we take the definition of mean field limit of function that was introduced by Lyon first in a mean field game context, but then it is now a very well-known definition also for kinetic theory, optimal control theory, and so on. And we have the theorem for convergence first by Lyon and then Cardet-Aliaguet in order to prove that if we have a function that is symmetric, I mean, if permutation invariant, if you change the position of the particles, I mean, in your vector, then you can have this mean field limit. And then in order to do the mean field limit of the kernel, we basically take the proof of the one for the function, and it is just a generalization for that. And you have again the convergence also of the kernel under some hypothesis, of course. We need symmetry in the first argument of the kernel, uniform boundedness, and uniform Lipschitz continuity. And so this is the theorem. So under this hypothesis that I just said, we can prove that there exists a subsequence and a continuous bounded kernel. So it is very important to see that the limiting kernel is actually a kernel. You can prove also this, such that this holds. So you want that for an increasing number of particles, the microscopic converges to the mesoscopic one, and then we have the supremum here to have to have the uniform convergence. I put also this diagram in order to give an intuition of other results, because so what I show now is this part here. So if we take a kernel and we compute the mean field limit of this kernel in the number of particles, then we have again a kernel. When I explained the definition of a kernel, you remember that I associated a kernel to an Hilbert space. So we can associate this kernel to an Hilbert space. It's reproducing kernel Hilbert space. The same we can do for the new kernel, because it is a kernel, so needs to be associated to a reproducing kernel Hilbert space. But what we can do is also go from here to here. So from this Hilbert space, we can take a representative function from this space, compute the mean field limit for M, and then we end up again here. And also it is proven from Christian Fiedler and Michael Hertie and Sebastian Tripp that if you take an element here, then under some hypothesis, then there exists always a sequence here such that the limit is a representative function here. So it is a commutative diagram. Okay, so now some numerical experiments that we did in order to give some numerical evidence to the results that we found. So I will show you two different models. First, a first order model, and then a second order model. So the first order model that is usually used for opinion formation. So you can think about xi as the opinion of a person, of the person I. And then we have this particular type of interaction. So P describes the interaction between the opinion I and the opinion J. And in this case, we consider this type of interaction kernel that is a positive interaction kernel. So describe attraction between the opinions. So the idea is that two persons that are close to each other, they start to share the opinion. To test the method, we consider the learning of the variance and the skewness of the particle system. So the variance, as you know, is related to the second order model. The skewness to the third, is related to the second order moment, yes, and the skewness to the third one. And the skewness is just a measure of the symmetry of your density distribution. So if it's completely symmetric, it's 0, otherwise can be positive or negative if you have the tail on the right or on the left. And okay, so we want to learn the variance and the skewness of this particle system. We apply the kernel method, so we know that we can write the approximation of the function as this weighted sum. We collect some observations. Up to now, I consider the case without noise, and the number of observations are capital N. So you know the mean and the variance only at some time step. Now you apply you can apply the method. There is actually a representer theorem that say that this function can be written like this. Here now it's just a linear system, so we can find our unknown alpha. And then we can use this alpha to learn the functional in all the other time steps. We choose a particular type of kernel for the kernel method. So this is actually, when a K is actually the kernel of the kernel method, and we consider this type of double sum interaction kernel that has the hypothesis in order to compute then the mean field limit. And these are some results. So in the first column, you have just the evolution of the opinions. In the second column, the approximation of the variance. And in the third one, the approximation of the skewness. Then regarding the row, I start first with only 2 measurements, then with 4, and then with 8. So you can see that the opinion, they are attracted between each other. So, and in this first case, we have just 2 inference points that are the points where we know the value of the function over a time frame that goes from 0 to 10 with 1000 time steps. So in this case, we know the variance and the mean just at the first time step and the last time step. And we can compare, of course, because in this case, that is quite trivial. It is easy to compute of the real variance and skewness. And in blue, we have the true variance or skewness. And in red, we have the approximated one. So you can see that the approximation is quite good. I will show you later a table with the errors. That is also going better, increasing, of course, the number of observations. So if you have more information, you have a better approximation in the end. Now, since we want to go to the limit for M for the number of particles that goes to plus infinity, we first consider much more agents from a microscopic point of view. So we just increase the number of agents or data inputs if you think about the learning problem. So in this case, the inference points are fixed to 8 in all the cases. What we change is the number of agents. First 10, first row, then 100, and then 1000 in the third row. And here again, approximation of the variance and approximation of the skewness. In this case, again, we have very good approximation for all the cases. And now I show you the table in order to compare the errors that we have for this case, where the number of agents is fixed, and for this case, where the number of agents is increasing. So this is related to the first set of pictures, and this is related to the second one. So you see that in the first case, the number of agents is fixed, and the number of inference point is increasing. So of course, also the error is decreasing because we have more and more information. Second set of pictures, we fix the number of measurements point, inference point, and we increase the number of agents. In this case, the error is not changing. So this gives us also an intuition that we can have a result that is independent from M, and we can actually have a well-defined mean field limit. So this was just increasing the number in the microscopic case, but we are interested also in the case when M is going actually to plus infinity. And so we did some numerical experiments also about that. As I said before, when you have a multi-agent system, and in particular the one that we consider here, sorry. If we compute the mean field limit of this, we end up with this partial differential equation, where this is a local term and P is the interaction kernel. And the mean field limit instead of the kernel, the double sum Gaussian kernel that I showed you before, is this one. We can compute the same steps as in the microscopic case, also numerically. Of course, we have to approximate the PDE. And these are, again, the results. So here, instead of the evolution of the particles, I have the evolution of the density distributions of particles. These are the points where I know the variance and the skewness, the inference point. And here, again, the approximation of the variance and of the skewness. So you can see that we have a numerical evidence also from a mean field point of view. Now, I want to show you other two applications, but we change a little bit the idea. So, no, sorry. First, second order model. So up to now, I'll show you first order model for opinion dynamics. We did some experiments also for the second order model that you saw already in some talks of today and yesterday. So second order model, so we have both the evolution of the position and the velocities. The system for the velocities is similar to the one of before, but now we consider a Kucker-Smale kernel with here the exponent equal to 2. And so in the pictures, since we are in a second order model, you see first the evolution of the position. So first we had attraction between particles. Now we have attraction between velocities. And so this translates in alignment between particles. So here we have the position that start as usual. I never told you, but I take always the initial condition uniformly distributed between 1 and 2. So it starts from here, and then the particles align over the time. If we look instead to the velocity, the velocities are attracting between each other. In this case, we have 4 inference points, and here I show you just the variance that is, again, well approximated with this error here. And so we have results also for a second order model. Okay, so now I think it's time to change. Yes. So now we change a little bit. So we are not interested anymore in computing the mean field limit, at least related to the kernel method. So, because if you remember at the beginning, I said that the function that we have to learn needs to be defined on the state space of the multi-agent system, because otherwise it's not interesting anymore computing the mean field limit. But on the other side can be interesting for other reasons. So what we did, instead of having the state of the particle as an input of the kernel, we have just the time. Sorry. So we have just the time as input. So in this case, you can observe that it's not trivial anymore to compute the variance, because if you have the state, then you compute the variance without problems. If you have just the time, you cannot compute the variance. So the learning problem can be useful on this aspect. If we compute the mean field limit here, we have the mean field limit of the multi-agent system, but we don't have a mean field limit of the kernel method, because it will be exactly the same. And so here I used again Kucker-Smale model. So alignment between particles and attraction between velocities. just to underline the fact that I don't know the state, but I only know the time, here I put the red dots in the inference point. So I know the variance, just the true variance, just in this point. And I can compute the kernel approximation, where now the input of the kernel is just the time. So you created an approximation of a function that you can give in input just the time, and as an answer, you have the value of the variance. Of course, is not good as when you have the information of the state, but still you can have an approximation depending on the context where you want to apply. Can be not a problem to have such an error. Staying on this setup, changing again the input of the kernel. So again, we are not interested in the mean field limit. We can apply this kernel method also to an optimal control problem. And now I show you how. So consider again the Cuckeres-Mail model, that is the constraint of an optimal control problem. And imagine that you want to minimize the variance. So this is a classical case when you have the cost that is a cost that goes from 0 to capital T, that is the final time. And here you have the variance. You want to minimize this functional subject variance or skewness. You want to minimize this functional subject to the this constraint, that is the Cuckeres-Mail model. And now, instead of solving this optimal control problem that can be very expensive from a numerical point of view, we approximate the function that we want to minimize using the kernel method. And the kernel now, we compute the kernel, let the kernel depend on beta, where beta is this parameter here of the Cuckeres-Mail model. So you are somehow looking to the best parameter of the Cuckeres-Mail kernel that give you a minimization of this functional. And you do it using this kernel method. So you have actually a surrogate model that is easier, of course, because you have now just a function of beta, and you can minimize this function using your, don't know, gradient descent method or whatever. And these are the results. So for the approximation of the variance, so here we have again the true variance and the approximated one. And in this case, we also did some experiments with adding the noise, because up to now I show you only numerical tests without the noise. When we add the noise, is a little bit different, the computation of the kernel, because you have to take into account that you have also a regularization term. And so, as we saw in the previous talk of Fornasier, we have to take into account also of the term that you have in front of the regularization term that will depend on the variance and so on. But this is just to show you numerically the results. So of course, in the noisy case, is not perfect. Anyway, if you are interested in finding the minimum of this function here, then you see, for example, in this case, here you have, I underline in blue the real minimum and in red the approximated one. And so they actually coincide. Also here without noise, they coincide. Here again, they coincide. And in this case, they don't coincide, but they are quite close. So for example, the optimal beta in order to minimize the skewness would be 2. And here you have 2.2, I don't know, something like this. Okay, so that's it. So just to conclude, what we did is we consider kernel method in the multi-agent system framework from a microscopic and mean field point of view, and we gave some numerical evidence. What we are planning to do now is to use kernel methods for neural networks, in particular for residual neural networks. And this is related to the last problem that I show you with the optimal control problem, because, you know, when you have a residual neural network, you have to find the weight, the optimal weight and bias. So you can see it as a control problem, and you can apply your learning methods to approximate the function. We didn't compute a rigorous derivation of specific kernels. So the one that I show you, for example, before, it was the one double sum, it was a formal derivation. So the idea is to compute a rigorous derivation, and also to study learning rates in the mean field limit. Some references, and that's it. Thank you for your kind attention.
So we do have time for questions. So are there any questions? Yeah.
In your numerical results, it seems that at the tails on the left and on the right, that you have kind of an implicit regularity assumption, so that it goes like a derivative to 0 at the bounds. Is it somewhere, or does it just happen maybe?
You mean here and here?
Yeah, so exactly there on the top left, it seems that it tries to go with a 0 derivative towards the bound.
Yeah, I think this is, so we didn't put this constraint, but I think this is like the usual problem that you have when you want to interpolate also with spline and things like this. And there are examples, for example, here, where is that is very evident, this thing. Wait. Okay, for example, here. So I think also because what we did is just to consider equidistant point, while there are some works, and maybe could be interesting also to do some studies to find the optimal position of this point in order to have a good approximation. Because, for example, here that the function is changing a lot, I mean, this happens, I think, also for this reason. But I didn't investigate that.
So then the optimality of the points would depend on the unknown solution, which is kind of...
No, I mean, I don't know, but
Sure.
yeah, we didn't take care of the optimality of the point. I think that this could be done instead of taking into account just the equidistance point.
Yeah, okay.
I think, yeah.
Thank you very much.
You're welcome.
Are there other questions? Okay, so maybe I have one. So what about the rate of convergence? Did you have a theoretical estimate on how much well they approximate?
No, it's not. So for the kernel method, we have convergence, but not rate of convergence, also in the literature. And yeah, so I don't know. I mean, I don't know, it's not done.
And did you just try with the Gaussian kernel, or did you try with something else?
Yes, I always try with the Gaussian kernel. So in the paper, we describe also pullback kernels because we need to have the assumption in order to then compute the mean field limit. So we have these two types of construction of the kernel in order to have the assumption. One is the double sum and one is the pullback, but all the numerical experiments are done with the double sum or with the Gaussian kernel. Yeah.
Okay, so there are no other questions. So we can conclude here this morning session. So thank you again to Chiara for the nice talk.
And so the difficulty is that if you want to explain this phenomena with ends, it's what I said. It's very simple. Cells are kept together because of chemotaxis. They are attracted by the signals they emit, and they move to the food. So in terms of waving ends, It's easy. You have two processes, one which keep them together, one which move them. The problem is that if you take the Keller-Segel system, you do not have traveling pulses like that. They don't exist except if you cook up everything to make them work. But in the situation we're interested in, you will not find traveling pulse for the Keller-Segel system. So there is something else which is at work here. And if you can feel, if you want to feel, to fit this experiment, the flux-limited Keller-Segel equation is doing a very good job. The flux-limited Keller-Segel equation is a variant of the Keller-Segel system, which was worked out by Hermann and Ottmer and by Dolac and Schmeiser, and where the flux, the drift, according to the one of the two quantities, the chemoattractant or the signal, is limited. There is some kind of saturation which made that you keep only a part, I mean, a saturation of the drift. And the same equations are for the chemoattractant and for the consumption of the substrate. If in some sense here you see that compared to the Keller-Segel system, the direction is playing an important role, and not only the value. So this is what is behind. And now, if you look at that, if you look at traveling bands, traveling pulses, which means solution of x minus sigma t, then you compute and you will find easily that this equation has traveling pulses. And not only you have traveling pulses, but you have very few parameters. I'm missing maybe the parameters for consumption here, but which are in Ks and Kc, so they are not very important. So you have them. You have very few parameters. You can fit precisely the signal, I mean the experimental signal, which is a random blue line, and the solution of the system, which is the purple line. And so this model is doing very well with this system. In particular, it is able to reproduce the asymmetry of the traveling pulse. And so the question now from a mathematical point of view is, where does this flux-limited Keller-Segel equation comes in from? And to answer this question, of course, you cannot write a macroscopic equation by itself. The best way is to go to a finer scale, and this is the run and tumble phenomena, so the kinetic formalism, which is used to describe precisely how individual cells move. And from this, you expect that you can recover the flux-limited Keller-Segel equation and explain why these flux limitations arise. I have forgotten to say that this was 20 years ago when Dolac and Schmeiser were doing that. This kind of equation, this kind of flux limitation in that time was very, very fashionable also because of image processing. In image processing, you have many, many equations where you have this kind of non-linearity, like in the minimum surface and things like that. And so there were many, it was a very active field in that time. Okay, so what I will explain is what are the kinetic equations used for run and tumble of bacteria. I will explain why the flux-limited Keller-Segel system comes in naturally as a macroscopic equation. I will explain why it's not enough, because now you have a kinetic model. Why do you write it like that? And that you have to go back to internal states. And at the end, if I have time, I will speak of instabilities. So the motion of cells by a run and tumble is an old story. It begins in the 80s by Alt, Dunbar, and Otmer. It was pursued by Angela Stevens and Tom Hillen, and has to do with the following things. Cells, bacteria, Escherichia coli, is moving because it has flagella. These flagella, they can turn and act as a propeller. So they swim, in fact, in a liquid. And these cells, well, they are well coordinated. They turn and they act as a propeller. At some points, these flagella, they are disorganized. And then suddenly, the flagella go around the cell, and the cell will turn randomly because of this disorganization until a new coordination of the flagella comes in and a new direction is taken. And the result of that is that the cells is moving with this kind of run and tumble phenomena, which means that makes jumps, turn, make jumps, and turn. The jumps are an order of magnitude larger than the reorganization stage, so the tumbling stage. Nowadays, people have a tendency to not to accept this assumption, but also time for the tumbling stage. Usually, it is taken as very short. If you want to see what it means in reality, this is what you observe. Okay, so what you see on these experiments are many, many dots everywhere. These dots are all the cells. There are maybe, someone was mentioning this morning, maybe 1 million cells. So these are the dots you see. Some cells have been engineered to be fluorescent. And so you see maybe 100 of these big dots, which are fluorescent cells. So those ones, you see them well, but the others are there. And if you follow these dots, you see random, if you follow these cells, you will see that they do these jumps and this tumbling. So some of them, it's very clear. So if you have to look at the movie a long time and follow some cells, and you will see they do that. But did you observe something else? So there is something which is very visible if you follow from the beginning, is that you have a light band in the middle, which is moving slowly to the right. And I'm sure you all know what is asymptotic analysis, but the effect is exactly this one, that you have this band, which is in the middle, which is the light band, which is the middle, which is produced by all the cells, which is moving very slowly to the right. And this is the macroscopic equation. So this is what an experimentalist would tell you is asymptotic analysis, of course. So if you want to describe this movement by random tumble, you have to go to kinetic equations. So I took two slides to recall you. I'm sure most of you know kinetic equations, but I would like to, of course, kinetic equations are characterized by the fact that you have that each cell have now position and a velocity. They are moving with the velocity xi, so there is this transport term which tells you how cells are moving, and you have the tumbling. If you do Boltzmann equation, I don't recall what is the Boltzmann kernel, but either you know it and you know it, either you don't know it. And if I show you the kernel, you will not learn more about it. The only thing I would like to point out is that the binary collision term in Boltzmann is a beautiful geometric object, which is parameterized by the sphere. And abstractly, it's a very nice object, which has many invariants related to the conservation of momentum and energy. And the formula, maybe you don't like them, but they're very beautiful in terms of invariance. Same thing, if you look at plasmas, you have Vlasov-Maxwell equations. Here I wrote Vlasov-Poisson, but you look at Vlasov-Maxwell equation, you have this beautiful equation coming with an energy, with invariance, and so on, which is marvelous. And if you look at scattering of neutrons and photons, you have also this structure, which is exactly what we will use. So the main difference between these examples I mentioned, plasma molecules, is that it is extremely complicated to follow molecules. And to say that to find the distribution of velocity in molecules is something complicated. I'm even not sure, maybe some of you know it, if it's possible to measure, to visualize the velocity of molecules in a gas. What happens is that in these experiments, because bacteria are much bigger, you can visualize the velocity, the directions, and the velocity of the cells. And here is a diagram which has been produced by this physicist in Curie Institute, which tell you which cells are going to the right, which cells are going to the left, up and down, and with which intensity. So you see that, for example, that in this part of the experiment, that the location where they do these measurements, cells are moving mostly on the right and not at all, not very much on the right, on the left. And so they can visualize that and they can measure this, which is the advantage of working with the big objects that you can measure, you can observe optically. So the standard equation for the kinetic equations, which have been written by Ottmer at the beginning, are the following. So you have this run phase, like in all the kinetic equation. You have the tumble phase, and the tumble phase simply is modulated by the chemical environment. So the C, the chemoattractant, and the substrate, the food S. And this will modulate the tumbling kernel, the scattering, if you want. While usually the scattering is given by external obstacles. That's the reason, the way neutrons are working. Here you have an external background that cells are measuring, and they react to these measurements. And many forms of this tumbling kernel has been given. I will keep for the first slides with the idea, for example, that cells can measure the concentration of chemoattractant because they have sensors on their membrane, and these sensors they add up during a certain time epsilon. During the jump period, if you want, the jump time, they measure this concentration, and according to the value of this concentration, they make a decision to turn or not to turn. So this is one of the examples which is possible. In any case, if you do that, and if you use the usual asymptotic analysis, it means that you rescale space and time in such a way that you get a parabolic scaling. What you obtain is the usual diffusion scaling, and it's not very complicated to prove that when epsilon converges to 0, the solution will converge to an equilibrium. So usually the velocity for bacteria, we take them on the sphere, on the circle in 2D, because they have a certain, during the jump phase, they have a given velocity, and only the angle is changing. That's not very important. So you have an equilibrium where you have a uniform distribution of cells on their velocity space, and you have a density, a number density of cells, n of tx, at the end. And when the chemoattractant, here I only use a chemoattractant, and this I forgot about the substrate, but it would be the same. The substrate will converge, and what you end up at the end are exactly the Keller-Segel equations. You obtain the Keller-Segel equations with a coefficient D, a diffusion coefficient which depends on C, which at least is new. I mean, Keller-Segel have no reason to put a diffusion coefficient which depends on the concentration of chemoattractant, and you have a sensitivity which is given by that. So if you want, this kernel is asymmetric in Xi and Xi prime because it only depends on the incoming velocity. The cell doesn't know where it will go. It's a random decision. So it doesn't know where to go. It only takes a decision on the way, the velocity it has before jumping. And this asymmetry is the reason of the drift. And the symmetric part, the K, is the reason of the diffusion. So if you do that, you are happy because you have found the Keller-Segel system, but you have not found the correct equation. You didn't find the flux-emitted Keller-Segel equation. So if you want to find the flux-emitted Keller-Segel equation, you have to be a little bit more accurate on the physics of the biology of the way cells are moving. In fact, cells are not changing their tumbling rate according to the chemoattractant. They do something different, which looks like the same, but which is not exactly the same. During the phase, the jump phase, they measure the concentration. And as long as the chemoattractant concentration increases, they are happy. And if they are happy, they will continue the same way. If they go in the bad direction where the chemoattractant concentration diminishes, they don't like it, and they will turn often, which means that when they are going in the direction of increasing chemoattractant, they make long jumps, so they will go far away. When they go in the bad direction, they turn, so they don't move until they find a new direction which is positive, and then they make a long run. Okay, and so this is the effect of chemoattractant. And this has been measured, of course, in biology. Which means that the kernel, K, is not a function of the concentration. It's a function of the variation of the concentration along the path. Which means that it depends on this quantity dtc plus Xi prime. So again, the Xi prime is the incoming velocity before jumps, and they will jump to the velocity Xi. So this is the kernel. And so now if you take this kernel, you rescale it, as I said before, with the diffusion scaling. And if you redo the asymptotic analysis, I will not do it. It's just Taylor expansions. What you can prove rigorously is that the diffusion limit of that is exactly the limit, the flux-limited Keller-Segel equation. So the fact that this quantity depends on the gradient, after scaling, when you rescale space and time, the DTC will disappear because you don't rescale space and time the same way. And then you recover only something which depends on the grad C, and this K epsilon will make the limitation, the flux limitation, the saturation of the flux. So this is the reason why the flux-limited Keller-Segel equation arises. And what you find at the end is a class of flux-limited Keller-Segol equation where the saturation phi is related to your kernel. Okay, if you give me K epsilon, I give you phi. There's a very easy formula for that. And typically, K epsilon is very stiff. I mean, cells either they run or they stop. There is no. They really take two values, K plus and K minus. Okay. But now the next question is that I recalled you what are the Boltzmann equation, what are the Vlasov-Maxwell equation, why they are so beautiful in terms of geometry, of invariance. And now I show you a model in which the K epsilon depends on the ugly quantity, which has no nice property. And so the question is, can we explain why this arises? And is this true? Postulating that cells are doing that, can we go further and explain this? And to do that, you can also do it by using the internal state, the way cells are taking decision. So cells have a membrane, which is a gray line. There is an outside world, and there is an inside world. So outside, what you have are the concentration of C and S. And the cells measure that because they have a transmembrane proteins where the molecules can attach. And when the molecules attach to these transmembrane proteins, they change the state, the physical state of the molecule, and they send a signal inside. And depending on the saturation of this, the binding on these proteins, the result is that these flagella will go in the correct direction and will be all together coordinated, or will be completely disorganized depending on this state. And so that's the way the outside world, the chemoattractant and the signal, the food, will communicate the information inside. And so to do that, now you have to take into account an internal state, which is modulated from the outside, which I called M, which is here. Now you have a kinetic equation where the variables are time, space, velocity, and an internal state, M. So the equations, and this is not this is not very surprising. There are many kinetic equations where you have internal state. For example, for droplets, you have the radius of the droplets, which is also a parameter you put in kinetic equations. So it's not something which is surprising in terms of kinetic equation. It's not new. So here, what you say is that you have a chemical reaction, and this reaction is, in some sense, a chemical reaction which adapts the internal state M to the macroscopic state C. Okay, so the outside will create a signal, which I call capital MC, and the reaction is to adapt M to MC. So you have a chemical reaction, which is more or less have a stable state, which is capital M of C. But of course, C depends on T and X because it depends on the dynamics of all this. So this is the chemical reaction part. And then you have the tumbling part. And the tumbling part is that decision is taken to jump or not, depending on the disequilibrium of the state, of the internal state compared to the outside state. So this chemical reaction, in some sense, is the reason of the chemical reaction, of the tumbling. So what we did with Bintang and Nicolas Vauchelet is to introduce two parameters. One to say that the chemical reaction is fast compared to the motion of cells, and that this decision is stiff, which is quite a natural assumption. And if you do that, if you take this equation depending on M, and now what I would like to say is that this equation is nice. It has all the properties you want in terms of invariance, in terms of geometry, and so on. It is an equation which has the shape of something which comes from physics. When epsilon converges to 0, this term will be dominant. You will get an equilibrium, which means that you will get a Dirac mass where the internal state is at equilibrium with the macroscopic state. And this will be multiplied by the standard kinetic equation F, standard kinetic function F. And this F satisfies exactly the kinetic equation with a kernel, which is the one we postulated. So this kernel, in fact, for the kinetic equation, is just the result of this asymptotic analysis. So what we said so far is that now you understand that you have a precise kinetic equation with internal state. This kinetic equation gives you a standard kinetic equation in the fast reaction limit. This kinetic equation, when you take the macroscopic limit, the mean free path going to 0, you recover the macroscopic equation, which is the flux limited Keller-Segel equation. So you have a complete chain on that. It turns out that all these equations share the same property, which they have instabilities and the ability of creating patterns. So the Keller to do that, to see that, and there have been many works about this subject also. You take the Keller-Segel equation and you put a right-hand side, where cells, now we look at a long time range, and now you don't neglect the depth and the growth of cells. And if you put this, you observe that n equal 1 is a steady state. If n equal 1, c equal 1, so grad c is 0, n equal 1, everything disappears. So n equal is a steady state, but it is known that the Keller-Segel equation, the steady state 1, is unstable for the Keller-Segel equation if the sensitivity parameter is the drift is large enough. This is also true for the flux-limited Keller-Segel equation. If you take the flux-limited Keller-Segel equation with the function phi, as I mentioned earlier, and if you do the linearized analysis, you obtain with this formula for the dispersion rule for the growth rate. And if this is positive, the steady state 1 is unstable, which is true when phi of 0 is big enough, which is the chi in the case of Keller-Segel equation. And always it is Turing instability, because when k is large, it cannot be unstable. The modes which are unstable are always finite. K large cannot be unstable, but if phi is 0, some k's will be unstable. And so this is also true for the kinetic equation. And that was funny because Shugo Yasuda, who did the computation, did it with Monte Carlo methods. And of course, you have to run a number of cells to see a solution of these equations, because you are in space x and psi in 2D. So he was running this code, and he was seeing instabilities. But of course, when you run Monte Carlo codes, you would see instabilities. And at some point, he was convinced that these instabilities are not numerical instabilities. They have to do something with physics. And so he used a big computer with a huge of cells. What you see here is the result of a Monte Carlo simulation, where obviously what you see is an instability. And of course, you can prove that the kinetic equation undergoes some kind of Turing instabilities when the parameter delta is small here, enough here, which plays the role of the chi in the other formula. So this kinetic equation has a Turing instability, just like the flux-limited Keller-Segel equation, just like the Keller-Segel equation. All of them create patterns in the correct range of parameters. I think it's time to conclude. I would like to say that it's not all. For those who like abnormal diffusion, you have a lot of articles explaining that Levy walks are playing a role in this. So there's another route for analysis of this equation. And I stop here. So the conclusion is that modeling of bacterial population is a very, very broad field. You have extremely different bacteria. First of all, here this was chemotaxis, but you have many other kind of bacteria, which are very interesting in terms of the way they create patterns. The flux-emitted Keller-Segel equation can be derived rigorously from individual-based models. And also that it is in this kind of fields, it is possible now with the experiments which are done to fit the experiments with the model, which is not so often in biology. And mathematically, there are many questions like singularities, asymptotic analysis, instabilities, fractional derivatives. So it's a fun, full of mathematical questions. I would like to conclude to thank all my collaborators. All this began with this group of people when in Vienna. Many works were done with biologists in Curie Institute in the center of Paris, but also in the Paris South, in microbiology lab, and with mathematicians that you see here. So I stop here. Thank you for your attention.
Okay, so thank you for this very nice talk. Are there questions from the audience? Okay.
Thanks, Benoit, for the lovely talk. The model with internal structure where you have the dependence on M inside the drift term, would it be possible to obtain a similar, let's say, macroscopic model if you were to include the dependence on M in a reaction term? Just to say that cells proliferate at different rates depending on their M, and then you get selection as a concentration to a Dirac mass, and then you scale up.
Thank you for the question. Very interesting question, by the way, because it. Okay, now we have to understand the time scales. The time scale for reaction, division of cells, is much longer than the time scale for the decision to run and tumble. Run and tumble. The run is 1 second. The tumbling is 1/10 of a second. The division of cells is minutes. Okay, so we're not the time scale. What I forgot to say, but now that you are still here, I can tell you all what I told you is wrong, because the time scale for the methylation is slower than the time scale for the tumbling. For many cells, when you register there are ways to measure the time scale for the internal state, and it is slower than the tumbling. So the correct scale would be to make a tumbling limit, so macroscopic, depending on M, and then doing the equilibrium in M. Okay, that could be another thing. I don't know if it has been done. I don't think it has been done, but for many cells, it would be like that.
Okay. Thank you.
Other questions?
So since you brought it up, have other timescales been considered, like other ways to scale the parameters, and do they give rise to different equations, I suppose?
Yes, one way is the abnormal diffusion. You could rescale differently the tumbling kernel. If the tumbling vanishes, then you have to rescale differently. So based on like in the papers of Stefano Ola and then to all these people We did it in the kinetic equations. That's a possibility. And another way would be to keep to first do the hydrodynamic limit, keeping the internal state itself, which would be reasonable also. And I think I guess there are certainly many other rescaling possible, which I cannot imagine now, but you can imagine that there are other ways to do it.
But mostly the choice is driven by the fact that you want to really model that particular biological phenomenon, and so one is led to considering that the one that.
Yes, that's because Escherichia coli is a very important bacteria because it is of medical importance. So many biologists work on that. They know a lot of things on it. But there are many other bacteria which exist in the world and which are not very much studied. And especially ecological bacteria are very important and not so much studied. We don't know so much about them.
Okay, thank you very much.
So thanks, Benoit, for the nice presentation. I wanted to ask you something about your final comments about matching the models with the data. You have shown that there are different levels of the modeling from the kinetic up to the macroscopic as usual. And I was wondering, can you also have, let's say, some matching also for models which describe the biology at the kinetic level, or you typically need to resort to some simplified approach?
No, that's possible. That's possible also. There are papers of physicists who do that. They have big codes at the kinetic level where they match their experiments. What they do is externally they modulate the chemoattractant, and they look at the response, and they can fit the model. And I think, I'm not sure, but I think Mintang has developed also codes like that. So I think it's possible.
Okay, thank you.
Other questions? Okay, if not, I think we can thank our speaker, Professor Perthame, again. Our next speaker is Dr. Martina Conte from Politecnico di Torino. She will talk about kinetic models for cell migration in heterogeneous environments.
Second. Thank you. Thank everybody for being here. And before starting, I would like to thank the organizer for the very kind invitation. It's a pleasure and actually also an honor for me to have the opportunity of presenting here some work we have recently done in collaboration with Nadia, looking at some kinetic model that want to describe the process of cell migration into different heterogeneous environment. So the first part of this talk, I would like to give you at least an idea of the problem and the motivation behind this work, both from the biological but also the mathematical point of view related to the choice of then the kind of framework actually into which we are gonna work. And then later we're gonna see the general framework and two specific applications will be developed in that direction. So I'm also very grateful for the wonderful talk we had before, because we already introduced it for some aspect of the biology and some aspect of the methodology. So let's start from the problem. Biologically speaking, we look at cell migration because cell migration is actually a fundamental process for a large variety of phenomena that goes from physiological to pathological condition. It is fundamental, for instance, during the formation of the embryo, so during embryogenesis, but also for wound healing if we look at physiological condition of our body. But at the same time, we know that the invasion of tumor cells into the healthy tissue is driven by cell migration, as well as the process of formation of blood vessel, normal or abnormal, is based on the way cells migrate. Therefore, you can understand that cell migration is a very complex phenomenon, and in particular, is not just the results of one mechanism, but usually is the results of the superposition of different mechanisms, and the way they actually interplay between each other is quite complex to understand, even from the experimental point of view. And many efforts have been done experimentally, try to capture and also measure both microscopic and macroscopic parameters, but still there's a lot the work that can be done in this direction. And for sure, mathematical model can somehow help to better understand processes or to get better insight into some process that experimentally can be hard to distinguish. In particular, cell migration is driven by different interaction between cell and microenvironment, among other factors. And here I listed some of the migratory behavior that the cells can have in response to different external stimuli. The one I listed over here, I'm gonna go briefly through them because these are gonna be then the one we are gonna focus for our application later. So we already heard, of course, about chemotaxis. So as we understand, it's just the process of cell migration towards the gradient of a certain external factor, certain soluble molecules in the microenvironment. So if this is a positive stimulus, just cells move in that direction. And experimentally, one element that can be quantified looking at chemotaxis is the so-called chemotatic index that simply refers to or relates to the angle between the average direction of the direction in which the cells is migrating and the direction of the gradient of this schema attractant. So second example, a second kind of migratory behavior a cell can assume relates to the so-called phenomenon of steric hindrance. Steric hindrance refers to the fact that the ECM density has actually an impact on the way cells are migrating, and the density of the ECM can reduce or improve the cell movement. Here I just listed, I recapitulate some experimental results, and in particular looking at the bottom panels. Here the experimental is shown how for 3 different ECM density increasing from 2.5 to 6 milligram per milliliters, the tracking of the cells show a reduced in the spreading. So the more the ECM is dense, the less cells are able to move and spread into it. And this is also evidence looking, for instance, the first panel where we have the mean speed of the cells that decrease while ECM density increase, and the same does the mean square displacement. So all this, there are parameters that experimentally can be measured. Recapitulate this effect of decreasing of or to reduction of movement of cells related to ECM density increasing. And the last example of migratory behaviors I listed before is the contact guidance phenomenon. This phenomenon refers to the migratory behavior of cells that are moving in a fibrous environment. So in this situation, usually cells tend to crawl along the fibers and therefore to follow the direction of the fibers in their migration. So in the process of orientation, they try to align to the fiber themselves. Here, there's another experiment or some experimental data that have been collected that actually want to show this behavior of the cells. And in particular, they have the experimental set is made up of combination of matrigene and collagen at different densities in order to create different area in the ECM where different alignment of the fibers. If we look, for instance, at one panel, for instance, this red panel, the experimentalist evaluated over here the distribution of the fibers in that spot. And in particular, if they look at the frequency of finding a fibers aligned in a certain direction with respect to the reference direction, that is the x-axis. So here, what we can observe is that basically in the red spot, we have fibers highly aligned along the vertical direction. And if we look then after at the distribution of the cells in the same panel, so we look at just the same color, the distribution of the cells quantified in the same way show how also the cells try to align, or the majority of them aligned along that preferential direction. The same can be observed if we look at the green panel. So here we have horizontal aligned fibers because the higher frequency of finding fibers is in direction 0 and 180 degree. And the cells recapitulate this, or they follow this distribution. So all these are evidence that actually these are phenomena that are observed in biology. But the problem is also to understand how they actually superimpose, when we have different phenomena, how they talk with each other, how a cell decide after to move when it receives different stimulus. how we can therefore approach, mathematically speaking, the model. As we also heard before, migration is intrinsically a multi-scale phenomenon because there are individual cells dynamics, there is the collective migration of the cells, and we somehow want to understand how to connect this level. How we can describe at the mesoscopic level the way cells are moving in order to obtain at the macroscopic level some dynamics that recapitulate the microscopic behavior that can be experimentally observed. And in particular, which could be the link between the individual level measurement and the macroscopic parameters. So just to give you an idea, when I talk about measurement individually and macroscopically, what we mean is that if at the microscopic level, what we can measure are speed or displacement of the cell, net displacement, we can track the cells. At the macroscopic level, what we can measure, for instance, are cell distribution or diffusion coefficient, but how these different parameters talk to each other, how the way one single cell is moving then at the macroscopic level has an impact on the way the overall population of cells moves. So I tried to recapitulate somehow the main question we would like to, or we try to address overall in these works. First of all, which could be an appropriate microscopic limit that reproduce the individual cells dynamics that we observe, and we already heard before the physics, the fundamental physics behind it that we observe related to the migration of bacteria, but also cells. Again, how the individual level measurement are going to be connected to the macroscopic one, and in particular, under which assumption we can really obtain this macroscopic description. And also, once we obtain them, understand when, like in the terms in the equation, and how microscopic dynamics influence the macroscopic one. So this is more or less the problem and the main motivation because we started to look at it. Let's see how we try to approach the questions. So as I said, as you see also from the title, we want to derive a kinetic description for this process that is based on these three different levels we just saw. So we start from the individual level of description when the cells are basically described as particles, individual particles with their dynamics, and this dynamics is described with random walk model. From the microscopic description, we're going to see how it's possible to derive the evolutionary equation for the distribution function of the cells. There is going to be the function P, depending on time, the position, and microscopic velocity. And of course, its dynamics, its evolution is going to, its equation is going to evolve in accordance to the prescribed dynamics given at the microscopic level. And then, under which assumption and certain limiting procedures are possible in order to obtain the evolutionary equation for the statistical moments of P. So let's start from the individual level. There are two big family of random walk model, and one can consider. I listed both, even if we are going to then rely on correlated random walk model. So the first class is the uncorrelated random walk model that, as the name said, are based on no correlated steps. And in particular, there is an alternation of the random walker between jumps and pauses. So it jumps, pause for a while, and then it jumps again. And these jumps happens in accordance to a certain jumps probability. The kind of random walk we consider are instead correlated random walk, in which different steps are correlating between each others, and there's an alternation of run and turning, basically, and jumps. The simplest or one of the elements of this category is the velocity jump process, the VJP. We are going to describe velocity jump process. There is basically a Markovian process in which what we prescribe is a certain transition probability for the individuals, the particles, the cells, to change its velocity. And in particular, this process is piecewise continuous, as I prescribed, the piecewise continuous movement in space, and these changes in velocity in the velocity space as a jump. And why this? Because, let's say one example of velocity jump process is the run and tumble motion we just heard to talk about. So as we already learned, it's basically a process that describes the alternation of movement of bacteria or cell. They move straight over a straight line with a constant speed, that's the run. And then there is the tumble, when they basically stop and reorientate, and they change speed and direction eventually. And they start again moving in a new direction. And these jumps are generated by a Poisson process. So we're going to describe this velocity jump process mathematically, considering that each individual, each cells, is going to describe by two random variables, xt and vt, x for position, v for the velocity. And the joint probability for them is given by the distribution function p. So for the variation of the, for the evolution of the random variable x, we consider a kinematic relationship where x at time t plus delta t is given by the position at time t plus delta t vt, where vt is the velocity at time t. While for the evolution of the velocity, so to evaluate the velocity at time t plus delta t, what we consider is a discrete in time stochastic process where we have a certain probability sigma to change velocity in a new velocity v prime at time t plus delta t, or a probability 1 minus sigma to keep the previous velocity. This sigma is a Bernoulli random variable whose parameters is mu delta t, where mu is basically the frequency of orientation of our cells, and it can depend on position. While the choice of the new velocity v prime happens, as I said before, in accordance to a certain transition probability t that can depend on both space and pre and post tumbling velocity in general. So from the microscopic dynamics described here that implements our velocity jump process, we can obtain the equation at the kinetic level, considering the averaged equation for a certain observable phi. So if we consider the rate of variation of this average, so phi evaluated, so phi depending on the random variable x and t at time t plus delta t minus phi of x and v at time t, and we expand this expression using the relationship given over here, so the kinematic relationship and our Poisson process for v, we get, simply reorganizing the terms, we get the last equality here at the end. So from here, if we consider the limit in which delta t tends to 0, what we can obtain is the instantaneous time variation of the average of the observable phi that gives the equation that you see here at the beginning. Now phi is our general observable, so we can assume that actually we can choose a certain observable phi such that the dependence on space and velocity can be factorized. So we have a product between a certain cx and phi v. And if we write down the weak form of the equation we just saw for the expectation of phi v, we obtain the equation that I see here in the middle, where again, you can see the appearance of the frequency of orientation mu and the transition probability t over here. This is nothing more than the weak form, the corresponding, if we consider the corresponding strong form of this equation, what we obtain is the classical equation for the distribution function p, depending now just time, space, and velocity, where p, just for recalling you, is the distribution function for our cells. Now the operators here on the right recapitulate the velocity jump process that we model macroscopically, and is given by this last row, and it basically consider again a loose term of cells that get velocity into v or lose it. And it's a typo, I'm sorry, but here is t of x, v, and v prime, because v prime now is the pre-tumbling velocity and v becomes the post-tumbling. So there was a typo over here. So that's the general way the kinetic equation can be derived from modeling a velocity jump process microscopically. From here, as I said before, it is possible, under certain assumption, to derive corresponding macroscopic equation for the statistical moments of P. In particular, what we are going to derive is the macroscopic equation for the cell number density rho over here. And the kind of macroscopic limit we consider, and here I want to stress out this point, is a certain macroscopic limit in which actually the moment equation for rho is going to be set on the same spatial scales of the experiment. So the spatial scales is going to stay to be the macroscopic spatial scales. And that's because we are going to see it in a while. One element of our approach is the including a non-locality in space. In order to keep this non-locality in the macroscopic limits, also because non-locality is a microscopic phenomenon, it's a phenomenon that we can observe macroscopically, we have to keep the spatial scales at the same scale of the of the experiment instead of rescaling it. And therefore, this scaling procedures is done considering L tilde, V tilde, and T tilde as usually reference length, velocity, and long time scale. So we consider a classical non-dimensionalization of the kinetic equation, as you can see over here, where of course we end up with the Strual number, St, and the Knudsen number. Now, as I said, we keep the spatial scales as the spatial scales of the experiment. So L tilde is of order 1. And assuming, considering epsilon as small parameters, we stay in a regime in which the Knudsen number is our small parameters. That's basically the high frequency regime. So assuming the Knudsen number to be the small parameters, the appropriate macroscopic limit we can perform is gonna depend on how the Strual number relates to this epsilon. So the Strual number is of the same order basically of the Knudsen number. The appropriate rescaling of the tilde of our long time scale is given by the expression that you can see here. That means our phenomenon is diffusion dominated. So what we're going to perform is a parabolic scaling to get the equation for the cell number density rho. Instead, if the Strual number is equal to 1, that they correspond to this macroscopic regime, there is a drift-dominated regime. So the drift is our dominating phenomenon, and therefore the scaling is going to be an hyperbolic scaling. How experimentally we can understand if our phenomenon is parabolic or it's parabolic or diffusion-driven or drift-driven? Well, we can look at the mean-square displacement of the cell. So if we look at the mean-square displacement shown in the experiment, we can observe if it's either linear in time or quadratic in time. If the mean-square displacement is linear in time, that means actually we have a diffusion-dominated phenomenon. Otherwise, if it's quadratic in time, what we actually are observing is a drift-driven phenomenon. And therefore, if we set the Strual number to be epsilon to the power 2 minus gamma, we exactly recapitulate what I just showed you this slide before. So we recapitulate the limit we want to perform. The scaling is based on the classical expansion of probability of the distribution function and transition probability. And what we can obtain macroscopically are either pure transport equation or diffusion drift equation, depending on first the kind of limit we can perform because of the way our phenomenon is microscopically, and also depends on either if this condition called solvability condition holds or not. So if microscopically we see a diffusion-driven phenomenon, so remember it means that the Strual numbers is of order epsilon, then if this solvability condition holds, that simply means the first terms in the expansion of the average of T is equal to 0, then we can get a diffusive limits that macroscopically is a diffusion drift equation where the diffusion coefficient is the first order terms in the expansion of the variance covariance matrix related to the transition probability T, while the velocity U1T is first order terms of the expansion of the average of T. Instead, if this condition doesn't hold, but still we have observed a phenomenon that is diffusion driven, macroscopically speaking, then what we can perform is a diffusive drift limits that leads to this diffusion drift equation at the macroscopic level for the cell number density rho. If instead our phenomenon is drift dominated, that means we can perform an hyperbolic limit that leads to the pure transport equation at the end. So that's the general framework that a lot of us already known. We applied this framework into different scenarios where we want to study two different models in which basically we want to look how an external factor, a factor in the microenvironment, is influencing the well cells migrating, describing this process into this framework. So we're going to see a first model I call single Q, because we have one external factor influencing cell migration, and then we're going to see a double Q model where we have two different elements influencing at the same time the choice of a new velocity for the cells. So the first model, we have just one external Q, there's the ECM, and there's a twofold way in which the ECM influence cell migration. On one side, because of the ECM fibers, there's an influence of the ECM into the choice of a new direction for the cell. And because of the steric entrance phenomenon, instead, there's also an impact on the speed or the new speed of the cells due to the decreasing or increasing ECM density. So we studied this interplay of contact guidance and steric hindrance, given that a cell is described by its position, speed v, and direction hat v. So we split velocity into speed and direction. And in order to describe the ECM, both at the mesoscopic and the macroscopic level, we first introduced the statistical distribution for the fibers, as it's usually been done, with this function small m, depending on space and direction, whose integral over the space of the direction give us the macroscopic ECM density at a certain point x, so this capital M. Of course, the ratio between small and capital M is a probability distribution for the fibers at position x in direction hat v that I introduced it also here because then we are going to use this concept also later. So there are two main ingredients for this model. One is the non-locality, and the other one is going to be the physical limit of migration. So non-locality, what does it mean? If we look microscopically at how cells perform sensing of the microenvironment in order to obtain information to it, and from this information decide where, if and where to move, when the sensing is performed, actually cells do not just rely on the information that it gets locally, so just around the main cell body, but the cells are able to extend protrusion, very long protrusion into the microenvironment that allow them actually to sense the external fields in a much larger area. This area depends on their sensing radius, as we call capital R. But in order to include this non-locality into the model, because it has an impact actually on the way the cell migrate, especially in certain situations like interface condition, we consider a non-local evaluation in space of the statistical distribution of the fibers. Then therefore that's gonna give us a non-local evaluation also the DCM density. And the information getting from this non-local sensing are weighted by a certain function gamma lambda, where this lambda is going to be lower or equal to the sensing radius. So that's the first ingredient, the non-locality. There is also one of the reasons for the observation I did when I was describing the macroscopic limit and the fact that we stay at the spatial scales of the experiment. The second element is the physical limit of migration. So on one side, cells perform non-local sensing. On the other, when they perform this non-local sensing, it's possible that they encounter certain region in which, because of the density, for instance, because of DCM, for instance, to be too dense, even if the cell would go in that direction, it cannot go because the cell nuclei has a certain stiffness, and under certain threshold, it cannot squeeze enough to move into the matrix. So if the matrix is too dense, cells cannot go in that direction. There's a physical obstacle that could be included, and the way it is included is basically modulating the sensing radius of the cells properly, and we'll see how. So these are the main ingredients of the model. How we model it, starting from the microscopic level. Now we have one variable for position that still follow the kinematic relationship, and two random variable for speed and direction. So V for the speed and hat V for direction. They vary according to the same discrete in time stochastic process based on the same probability sigma. So in this case, we assume that either cells change speed and direction, or it doesn't. It cannot change speed and following the same direction or the other way around. This sigma is a Bernoulli random variable with parameters mu, delta t, and now we have also times a certain kernel, interactive kernel B. We have to include this kernel because we want to model non-locality. So the fact that the cells actually are interacting as a particle with DCM, but DCM located at a certain location also far away from the cells. So if we indicate with YT the position random variable for the fibers, and V hat M the random variable for direction of the fibers, this Posner kernel is modulating the fact that a cell's an individual at position XT is interacting with an individual at position YT that can be distant from it up to a certain distance, capital R, so our lambda. And here is the place where actually our physical limit of migration is going to be included, because, and then I will come back later to the distribution, the support of B is compact, and it is actually defined by the integral 0 Rm. Rm is a modified sensing radius, so it's not a constant sensing radius, but it depends on space and direction. So as I was saying before, given a certain direction, a cell extends the protrusion, and as soon as the cells encounter a certain region in which cannot move into it because of the ECM to be too dense, then the sensing radius is reduced and is equal to the inf of this lambda that actually basically the region at which the cells can move. Instead, if in performing this sensing, actually the cells doesn't encounter any region that makes an obstacle for their migration, then the sensing radius will be maximum and will be equal to capital R. So that's about the interactive operators. What about the new distribution for speed and direction? So where I choose this new speed and direction? Well, the new speed V prime is going to be distributed following like following a certain probability distribution psi, and psi is a conditioned probability, is conditioned by the value of the ECM density at location yt. Instead, the new direction of the cells is going to be the same of the fibers located at point yt, so it's going to be equal to v hat m, and v hat m is distributing following the statistical distribution of fibers shown you before at position yt in direction v hat m. So that's the macroscopic model, and we already saw before that it's possible from it to derive the kinetic equation in the same formal way we saw. And now the kinetic equation for the joint distribution P for time, position, speed, and direction as a turning operators on the right. There is the same element we had before, so a certain turning rate, a certain transition probability. But here, the frequency of orientation eta is given by the product between the constant frequency of orientation mu that we had in the Bernoulli random variables parameters and a quantity, there is a capital M bar. This capital M bar is a weighted no local measure of the ECM density in a certain neighborhood around the cells. And instead, the transition probability T, that doesn't depend on the pre-tumbling velocity, that's an assumption, is given by the product between the probability distribution for the new speed and the new direction, as you can see with the local evaluation in space of the fiber distribution and the ECM density value. And the integral is given between 0 and the modifying sensing radius Rm. So it can be limited or up to the maximum one, depending on the point and the direction. So these are the element of the kinetic model, and from it, looking at the experiment and seeing which is the appropriate macroscopic limit, we can derive either a pure drift equation or a diffusion drift equation, the way I showed you before. But I think that very interesting is another element of this approach that's from the way the model is built, it's actually possible to derive also some statistical quantity that can be used then to compare the model results with some experimental results. And these quantities are, for instance, the index of directional persistence indicated by psi d, that basically gives a measure of the orientation angle of certain individual for each given microscopic velocity hat v from which a cell is orientating, where here ut is the average velocity of the orientation process that described by the transition probability t. And using also psi d, what is possible to compute is the expression of the mean-square displacement. There's something usually experimentally is often evaluated, and is also from the mean-square displacement that experimentally we can distinguish between a driven or a diffusion-dominated phenomenon. And the mean-square displacement has this expression depending if psi is different or equal to 1. And I just want to point out two elements of this expression because it's going to be useful for the next slide. Because if you look at the expression of D in the first case, there is both the presence of mu, there is the frequency of orientation of the cells, and of this calligraphic S square that's related to, that's the second order the second moment of the distribution of the speed. So that's an impact on the mean square displacement of the two elements, our speed, distribution of the speed, and the frequency of orientation. And why that's important? Because the first numerical test we performed with this model wanna somehow show how each element we include in the model is minimal in order to recapitulate specific macroscopic cell behavior. So we use our model, we simulate our model in three different cases. The first one is random fibers, uniform speed distribution, and we simply have a dependency on the ECM density, capital M, into the frequency. So remember, eta is M times mu. The second case, we have the dependency in speed and frequency, but still random fibers. And the third case in which we have aligned fibers and M dependency, frequency, speed. We want to recapitulate these two experimental results related to the mean square displacement that, as we said, decrease while ECM density increase, and the cell tracking that, as you can see, we see a reduced spreading while ECM density increase, and the spreading is also happening in a specific, so it's greater in the x-axis than in the vertical axis. So if we compare case 1 and 2, starting from the mean square displacement, we obtain these results. And it's pretty clear, since now we know the expression of the mean square displacement, while in order to obtain this pretty clear decrease in the mean square displacement, we need to have also an M-dependent frequency. An M-dependent speed. Just the dependency in the frequency is not enough. It is because we already saw how the mean square displacement actually can be computed. So M-dependent speed is the minimal element needed to recapitulate these behaviors. But if we look at we track the particle moving, then in this case, so still case 2, we recapitulate the reduction in the spreading, but not this asymmetric spreading. So more spread along the x-axis than the y-axis. To recapitulate also that element, the minimal ingredient we have to include is an alignment along the x-axis. If we have also fibers aligned horizontally, then we recapitulate both the reduction in the spreading and this preferential direction for migration. A second test we would like to show you before, just briefly go to the second model, concern this experiment. So here, the experimentalists analyzed how long take to the cells to move from this white region towards this empty cavity on the right in 2 different scenarios. So for 2 different values of the ECM, the underlying ECM. I hope you can see it, but in green, you have the experimental results that basically the one I just said, that in the first case, when M is equal to 2.5, cells need around 8 days to reach the cavity. So there's a finite time in the time window of 10 days they look at which cells reach the cavity. Instead, when M increase, well, the cells are not able to reach the cavity before in the time window of the experiment. So we wanted to use our both microscopic and corresponding kinetic description to see if, at least qualitatively speaking, we were able to recapitulate these dynamics. And in fact, in both cases, either the magenta and blue line, referring to microscopic and kinetic model respectively, are able to show that the time cells need to reach the cavity increase while ECM density increase. So that was the first experimental validation of the approach. But then we went further and we used our model to actually get deeper insight into the process without comparing it actually to other experimental data of this style. And we performed numerical experiment to look at the mean square displacement here, and then also the profile evolution of the solution, and compare microscopic, kinetic, and corresponding macroscopic limit. So in this case, of course, the microscopic model was simulated for a very large number of particles and molded at T in order to recapitulate the kinetic limit. And in fact, the 2 mean square displacements, still magenta and blue, they're pretty in a very good accordance. Instead, they do not, they're pretty different from the mean square displacement we can get performing either a diffusive macroscopic limit, the green, or an hyperbolic regime. And that's because if we look at the either microscopic or kinetic model and the way the mean square displacement evolved in time in that case, we can see that initially it seems that the behavior of the mean square displacement is more quadratic in time. That means a drift-driven phenomenon. At the end of in the last part of the simulation, it seems to be more linear. But overall, actually, neither of the 2 regimes is able to recapitulate the entire dynamics. So the dynamics is much complex if we look at it from a lower level of description, and therefore simulating and studying kinetic model allows to be able to keep this level of details and to get more insight with respect to looking just, I would say, at the corresponding macroscopic regime. Somehow we can lose part of the information. So one has to be aware of what can actually get lost. And the same is also recapitulated looking at the profile. So these were just 2 of the tests we performed with the first approach, but I also wanted to show you what we did with the double Q model. So if in the first case, we have 1 external stimuli, ECM, influencing in 2-fold way cell movement, here we have 2 external forces, two external stimuli, ECM and a chemoattractant. And we want to understand the interplay between the chemotaxis that is dominated by the chemoattractant and that is driven by the chemoattractant, and the contact guidance phenomenon that depends on the ECM in terms of fiber direction, so ECM fiber direction. So again, cells described by X, so position, speed, and direction. Now the 2Q are given by, for the fibers, the probability distribution we just saw before, the Q, where we assume that fibers are not polarized. That means this relation holds, so it's symmetric with respect to the direction hat V. And instead, for the chemoattractant, we consider a fixed chemoattractant profile that's a strictly positive function. We keep the non-locality in the model, so we have a non-local evaluation in space of both the chemoattractant and the fibers, but we do not consider here any physical limit of migration. So the sensing radius is all the time maximum and equal to the sensing to this value capital R. For this model, we directly formulated at the kinetic level, and we propose two possible transition probability describing the way cells change their velocity. Either so in the first case, what a cell can do is what we called non-local independent sensing model. So it basically responds in a kind of independent way to the information that gets from the chemoattractant and to the one that gets from the fibers, and it weights this information in principle in two different ways using the function gamma S and gamma Q. So we have basically the product between two directional sensing, one concerning the chemoattractant and one concerning the fibers. That's the first possibility. A different possibility is what we call non-local dependent sensing model, in which instead the cells choose the new direction for migration. Remember here, the cues are just influencing cell direction. The speed is not gonna change with respect to them. So the choice of the new direction depends on a unique weight of the information that the cells get from chemoattractant and from the fiber. Besides the speed distribution, and then we are going to assume a just uniform distribution for the speed with a certain mean, capital bar U. So here the sensing function are gamma S, gamma Q, and gamma are with compact support into 0R because we have no physical limits. And what we did was to see in the two cases which kind of macroscopic regime we can get, and we can also compare how they actually which kind of dynamics of the cells can emerge from them. So for performing the macroscopic limit, we introduce some reference length of variation for S and Q. And in particular, we look at the ratio between the sensing radius of the cells and this reference length of variation. So defining the parameters eta S and eta Q as the ratio between R and LS and Q, respectively, it is possible to have a first, we call when eta I, either eta S or eta Q, is greater than 1, we talk about a fast varying Q. When eta I is lower than 1, we talk about a slow varying Q. And in particular, the first differentiation between diffusive limit and hyperbolic limits come from how Q are varying. So a diffusive limit is allowed only when both Q are slow varying for the solvability condition. While instead, if at least one of the two Q is fast varying, then the limit we can perform macroscopically is an hyperbolic limit that leads to a drift-driven equation. In particular, it is also possible to introduce a new parameters eta, given by the ratio by eta S and eta Q, that allow us to give a first separation, like before you look at the dynamics, between which could be a chemotatic dominating phenomenon and a fiber dominating phenomenon. And if eta is greater than 1, the dynamics is gonna be driven by the chemoattractant, while if eta is lower than 1, the dynamics is gonna be dominated by the fibers in different way, depending on the type of limit we can perform. So let's see numerically some comparison between this macroscopic limit. Here we have different chemoattractant profile. There are it's the same Gaussian, same center, but with different variants in order to obtain different value for eta S. And instead, so these are the fixed profile for chemoattractant. Instead, for the fibers, probably is not very clear, but fibers are aligned along this diagonal direction. That's basically the perpendicular one with respect to the direction of the gradient of the chemoattractant. That's the other. And the fibers are highly aligned at the center, and the strength of this alignment decrease while we move towards the boundary. So it's basically described by a Gaussian. So with this ingredient, we compare, I'm going to show you two comparisons, just for the no-local independent sensing model, but are similar for the no-local dependent sensing model, just for a matter of time, between the case in which the 2Q are fast varying and the case in which the 2Q are slow varying. So for fast varying Q, when both eta S and eta Q are greater than 1, as I said before, we are going to perform an hyperbolic limit. And the limit equation for the cell number density rho is given by this pure transport equation on the right, where the velocity ut, as you can see, is basically the product between the no-local evaluation of the chemoattractant and the fibers, where information are weighted with two different functions. And this capital bar U is the mean speed that I saw before, the mean speed for the speed distribution. If we look If we look at the numerical results, we can see that the cells initially, I didn't put initial condition, but there was a Gaussian here in the bottom left corner. The cells start to move toward the chemoattractant because that's the case in which the dynamics are chemotactic dominating, eta is greater than 1. They move in a pretty compact way, and when they reach the location of the fiber, where the fibers are highly aligned, so this at the center, thanks to the non-locality that come out at the macroscopic level, as you can see here, they are able to feel that actually this also obstacle for their migration is somehow limited in space, and they're able actually to overcome the obstacle, to turn around it, and to reconnect on the other side and move towards the chemoattractant, instead of somehow getting stuck because of the obstacle. If instead we have two slow varying Q, so eta S and eta Q both lower than 1, but in particular now eta was also lower than 1, means a fiber dominating dynamics, we have the macroscopic level a drift diffusion equation, where the diffusion coefficient is given by the product of the energy of the speed distribution and the variance covariance matrix for the fibers, while the velocity is a sum of two terms, each of them considering the spatial variation of fibers and chemoattractant. That's an additive effect of them. This diffusive equation, so the simulation related to the kinetic equation that leads to these limits is recapitulated here on the right. Same initial conditions, so cells located here at the bottom on the left. But now, because of the diffusion, we can see that either in the first, I would say, time step, that the same time step of the previous simulation, cells almost have covered half of the domain already. So diffusion is very bigger impact. And moreover, while they're still keep moving, what we can observe is that instead of moving towards the chemoattractant, they start to align along the direction given by the fibers. So now the dynamics are dominated by the fiber distribution. So I just want to show you a last test before concluding that refer to the analysis of cooperation and competition between Q. So as I said, we have two Q, both influencing orientation. So it's normal to ask ourselves, is it the effect of the 2Q is kind of an additive effect, or instead there's all the time a Q, Q are competing if they have different direction, and if they are competing, what is actually winning and why? So we found this experiment in which the setting is basically to have cells located at the centers, cells were tracking over time, and they have two different situations. All the time in vertical chemoattractant, where the gradient goes from top to the bottom, and on the left, horizontal aligned fibers. That means the two Qs are perpendicular to each other, and instead on the right, they have fibers horizontal line on the left, vertical line on the right. So here they have two parallel Q, basically. So as you can see, there's not really an additive effect. So in the first case, if it would be additive effect, we would see cells moving diagonally, for instance, in average direction between the vertical and the horizontal one. But instead, they stay horizontally. So that's one Q winning, or there's competition and the fibers has a greater impact. So we use the model to recapitulate this. So this is a kind of justify the choice of having this product between the Q instead of the sum. And at the same time, we use the model. The model is able, therefore, for the way it is built, to recapitulate both situations. And if we look actually also at the mean speed along the vertical axis in the two scenarios, we see that for parallel perpendicular Q on the scenario on the scenarios on the left, the mean speed along the vertical direction basically go to 0. So cells stay horizontal; they do not move vertically. The fibers are aligned; it's such strong that doesn't allow cell to move vertically. So let me recapitulate what we have done. We have proposed a kinetic framework to describe cell migration, and in particular that allow to include this multi-scale inherent nature that cell migration has, and also allow to get this connection between individual and macroscopic level measurement that experimentally can be actually obtained. And in particular, the two model, but in general, the framework proposed is able to study the superposition of mechanisms that is very hard sometimes to study experimentally. So designing platform that can study superposition of mechanisms is not that easy. It is not clear what is influencing what when we do go to the experiment. So that's important to have at least an idea what can happen from the mathematical point of view. And the numerical simulation, at least partially, I hope showed the feasibility and potential applicability of this approach. There are different perspectives, and I'm pretty sure some of you already noticed some gaps in the description that we would like to fill. And the first one is, okay, the first model was derived from the microscopic level, but what about the second one? I propose to you a formulation directly at the kinetic level. So for sure, what we're planning to do, we're trying to do, is to actually derive also the second model from a microscopic level, but in general, to be able to define microscopic dynamics that leads to different sensing strategy at the kinetic level. So we have derived the no-local dependent sensing model, but what about the no-local independent sensing model, which is the microscopic dynamics that give us kinetically that kind of operator. And then second aspect, in the first model, we have fibers described with the position and direction. And I show to you two random variable, yt and v hat mt. So this seems to depend on time, but actually the ECM is fixed. So that random variable doesn't evolve. In reality, actually, ECM evolve. So what is going to happen with the time varying ECM? First, which could be the microscopic model that would realistically describe the variation of the fiber direction, for instance, and how including such variation would affect then the cells migration. That's something in the plan to do. So thank you very much for your attention, and I'm very happy to take any question or comments.
Thank you, Martina, for your talk. Questions from the audience?
I have one, but is probably at a very basic level. So I found really interesting this multi-scale behavior between hyperbolic and parabolic, which you try to describe with success. What I did not understand, and I would like to have some clarifications. There is one parameter, so one of the two numbers, which is set equal to epsilon. Are all possible ranges of mutual interactions among the two parameters considered, or you simply put one equal to epsilon, the other one is 1? No, so or also fractional scalings are possible?
The Knudsen number is fixed to epsilon because we are in the high frequency regime. That's why we fix the Knudsen number as very small parameters. And then we look at the structural number, how it is related to it. So that's the two scenarios that can emerge. Probably there are others, as we also saw before, that could be different scaling. These are two main.
Okay, because I would expect, at least from the point of view of mathematical analysis, that there could be some, so you have a first regime, a second regime, and there is a transition in between where you might observe something mixing the two effects. Is that possible, or either the one or the other? So what can be expected if you thought about this?
I have to say I'm not sure, I have to admit. I would like to think about. So when we look at the simulation with the mixed displacement, we saw that there should be something intermediate. So somehow we see transition when we look at a lower level of description from one regime to another. Then which kind of scaling can be defined in order to obtain the transition macroscopically? that's the question. I'm not sure, I have to say, but I'm gonna actually think about it. I'm sorry.
No problem. It's my curiosity and maybe some suggestion for the
I would
future.
say yes, but I don't know.
Thank you.
Other questions, comments?
Just if I understand well, the equations are always linear because only the external field is playing a role.
Sorry?
The equations are always linear.
Yes, yes.
How would you include the action of the cells on the matrix itself? Would it be possible? Would be delocalized?
Yeah, you mean so to have a variation also of the factors, and what's like what we said in the last perspective. So yeah, would be, so we would like to look at how cells are varying the ECM and how the variation of ECM is going to have an impact on the cell migration itself. So the idea would be to start from microscopically, try to model with stochastical process the way the fibers are gonna be modified by the action of the cell. How this is going to, which kind of operator is going to emerge then kinetically, we will see. I don't know. Probably it's going to be something nonlinear that then would have some problem when we look at quantity that are preserved and then the corresponding limits. Yeah.
What do you expect out of it? I mean, what are there experiments where you can see what is the effect?
Usually, okay. So if I remember some experiment I've seen, so there are two aspects when we talk about ECM variation. So sometimes there is just the degradation of the ECM. Sometimes what is modeled is degradation and remodeling. And that remodeling, I wouldn't say it's well understood, but there is a part of the biological experiment that says that the way cells remodel ECM is basically degrading the fibers and realign them in order kind to make a highway for them. So that would increase the speed and velocity in which they are varying. That is one possibility, or at least the one I have been working or read more about. But this remodeling of ECM is a very tricky process because it's not really clear what is going on with the matrix that is being degraded, how it can actually rearrange. For instance, tumors, as I read, that sometimes what they do is to rearrange ECM in order to make them an easier way into it. When there is an obstacle, they degrade and remodel it in order to make easier way through the matrix. When in the case like abnormal cells.
Any more questions? Okay, if not, we thank Martina again. Okay, so welcome back. We are ready for the last talk of this afternoon session. It will be delivered by Professor Mattia Zanella from University of Pavia, who will talk about kinetic modeling and control of epidemic dynamics in the presence of social heterogeneities. Please, Mattia.
Okay, thank you, Andrea, for the introduction. I would like to thank all the organizing community, the organizing committee for the kind invitation here to this nice workshop. And today we'll speak about some recent results, well, recent and less recent, I have to say. Since you see that the list of collaborators is pretty long, and indeed this project started in 2021, 2020, and then the first published paper is 2021. And then there is we won a national project on these and other subjects actually on epidemic dynamics, and it is still running. So I start. We have seen during this workshop, and we will see, I think, also the next days, that the kinetic equation may be employed in an heterogeneous, let's say, in heterogeneous fields. Let's say, starting from the original field of rarefied gas dynamics, going to some, biology like a swarm of birds or collective motion of ships or something like that, to pedestrian dynamics and traffic like dynamics. So the reason of this success is, I mean, there are many, but one of the main reasons of this success is the flexibility to link agent-based perspective to emerging macroscopic dynamics. And indeed, at the macroscopic level, we may have data with which we calibrate, let's say, our dynamics, and with which we may verify whether our microscopic view is feasible or not. Okay. Once we move from rarefied gas dynamics to the field of social dynamics, or let's say interaction between agents that are not particles of a gas, the interaction forces are not universal as the physical one. It's pretty known, and for this reason, in order to make, I mean, to use the available data, we have to introduce some degree of uncertainty. And for this reason, what will be done in the following slides has to be seen with the glasses of uncertainty quantification. And the uncertainty quantification for kinetic equation is a growing field. And you see here some citation of people working in this field. And indeed, I mean, what we will see at the end of the talk makes use of numerical methods for uncertainty quantification for kinetic equation, but we will not enter too much into details of this. The real point is that all the interaction forces have to be thought as uncertain. And then from the very beginning of the modeling, some degree of uncertainty is embedded in what we will see. Okay, so this is not new anyway. I report here a citation by Prigogine and Herman, where, I mean, I think that traffic modeling has been one of the first applications of kinetic equations outside the classic field of rarefied gas dynamics. And indeed, in this book that they wrote about this, they said, whereas in physics, molecules are exactly alike, even the individual properties of a human population are subject to statistical fluctuation. This means that indeed, I mean, today we say that this is due to some uncertain interaction forces or some degree of uncertainty that enters in the interaction between agents. Okay. In particular, we will treat not classical, I mean, swarming dynamics, but we will embed the world of kinetic models in a new field. It is, I mean, it's not a new field, but kinetic models in epidemic dynamics is a pretty new application of kinetic equations. Okay, so why want to do that? Well, actually, because disease transmission is done through interaction between agents. And so we have the possibility to, let's say, overcome the difficulties coming from classical views on epidemic dynamics. For example, in the recent pandemics, we have seen an explosion of compartments and different applications. You see Siddhartha, every letter is a compartment, actually, and then they supposed to know the transition between each single compartment with which they subdivided the population, or Sepiar is another compartmental model based on ODE. Okay, so our guess is to define in a, let's say, kinetic perspective the transition rates between each single compartment. Okay, so the compartmentalization of the population is not the point for us. We will stick to very simple compartmentalizations of the population, but we will try to, let's say, understand better how people move from one compartment to another. Okay, so this objective, let's say, is not new, and there are several groups working in this direction, seeing epidemic dynamics as a multi-scale process, starting from a microscopic perspective, where indeed the infection takes place, to the so the microscopic perspective to the level of observable data. Okay, so here there is a bunch of citation of people working in this direction, like Andrea Tozin, Nadia Loy, and Rosario Della Marca. They published several papers in this direction. Okay. Okay, why we want to do that? Well, because essentially where the infection takes place is at the macroscopic level, but we have to determine some, let's say, non-pharmaceutical intervention, classically, such that we dampen the action of the infection at the collective level. So the collective compliance with these measures has to be seen at the macroscopic level, starting from let's say a modification of the interaction taking place at the microscopic level. Okay, why it is so important? Well, actually, here you see a couple of pictures where we see in the first one a reconstruction of the infectivity level of each individual that has been done thanks to an interaction between our group and another group of clinical doctors led by Professor Baldanti. And actually, how we are infected changes in time, okay? And essentially, the peak of infectiousness takes place some days after we have been infected, okay? So that's why if we have to set up a non-pharmaceutical intervention, we have to be pretty sure that everybody will be comply with this intervention, since when symptoms develops, essentially during the peak of infectiousness, we have already infected several other people. So the only way probably is to dampen the level of contacts of the whole population, such that we dampen also the infectiousness of the global population. Okay, so that's why it's so important to understand how people meet and how people interact. Here is a second plot where we report the distribution of contacts. It is an experimental picture, this one. So this team of Bureau and collaborators, actually, they measured how people interact, in the sense that they measured how many people you interact you see every day. So this is the distribution of the number of contacts of a standard person in this experiment, and they say that this distribution is a gamma-like distribution. Okay, so it is not surprising that a gamma-like distribution has slim tails, and indeed, it's not really easy to have a fat tail distribution. Indeed, especially in an experimental view. So the idea now is to use a kinetic perspective to describe some contact formation dynamics, such that at the asymptotic level we describe again a gamma-like distribution, to see how this gamma-like distribution reflects at the macroscopic level in a compartmental model. We will use a prototypical compartmental model that is just the SIR model, but in any way it can be easily extended to more complex compartmentalization. As I said, that's not the point. We want to determine the transition rate between compartments that are inspired from a microscopic perspective. So okay, this is also has been also measured during the recent COVID-19 pandemic, where people measured the baseline period. During the baseline period, the contact distribution in Wuhan and Shanghai, and then they measured after the cordon sanitaire measure in Wuhan how the contact distribution changed in time. Okay, so essentially in Wuhan the government imposed some restriction on the contact between agents, and the same behavior happened also in Shanghai without any, let's say, superimposition of this cordon sanitaire. So the spread of information in the country, it seems that had an effect, even if there was no central government policy regarding this in Shanghai, indeed. At least in the very, at the beginning of the pandemic. Okay, so how can we describe from a kinetic perspective this behavior? Well, our idea was to, let's say, keep the compartmentalization present, okay? And then we determine kinetic distributions, then we call it Fj, that depends on V, that is the number of social contacts. Essentially, what is V is the x-axis, okay? So V is the number of contacts of a single agent. Okay, and time. So essentially, time depends on the kinetic. It's a kinetic time, and we will see how can we rescale this kinetic model such that this time becomes a macroscopic time. Okay, so the standard assumption is that the summation of all these Fj is a distribution function, as you see here. So if we sum over all the compartments, essentially, we don't lose mass. We can also define local moments. So for the alpha, I mean, as usually done in kinetic theory, so the local moments of order alpha are defined as follows. So it is the moment of, I mean, v to the power alpha fj. Okay, so in the following, we will indicate mj, the local mean of the distribution fj. Okay, so let's start with the kinetic model. As we said, there is the time of contact formation dynamics and the time of the epidemic. Okay, they are decoupled, as we have seen in the picture between Wuhan and Shanghai. Okay, the contact formation dynamics may be very fast, whereas the time of the epidemics is slow. Okay, so we decouple these two processes by introducing, let's say, a local incidence rate that is given by kappa and a contact formation operator that is it will be a kinetic operator is Qj. So Qs, it is the contact formation inside the compartment S, Qi, the contact formation dynamics inside the compartment I, and so for the R. Okay, so here the compartmentalization is the classical, as you see, SIR compartmentalization, so that susceptible can only be infected can only be, I mean, they will be removed after a certain time, 1 over gamma, and then the recovered can only gain, let's say, agents in time. Okay, so there is no reinfection in this simple model. Okay, so let's define what is kappa. So kappa is the local incidence rate, as I said, and it takes into account the presence, the presence of contact formation dynamics. So if we have a lot of contacts, essentially, it is highly probable to get the infection. If you have 0 contact, essentially, you will not get the infection. That's, the standard requirement. So a possible form of this Greek kappa is proportionality coefficient, v to the power alpha, v star to the power alpha. Why? Well, because if susceptible and infected have both lot of contacts, then it will be highly probable to get the infection. Okay, if they have one of the two people in the compartment have 0 contact, essentially the infection will not be transmitted in time. Okay, so other form of kappa, of course, are possible, and we will stick to this one. Okay, so now we have to determine what is Q. So Q characterizes the thermalization toward that gamma type distribution. So it considers the mass, and it is possible to see that, under this assumption, essentially, if we integrate in time our model and the local incidence rate does not depend on the contacts, so if alpha is equal to 0, okay, so we recover the classical SIR model. So SIR model is inside what we have written, okay, at the level of the evolution of mass fraction. So we integrate, so we have the evolution of rho s, that is minus beta rho s rho I, okay, so it is a classical SIR function, okay, but it's not very exciting anyway. So the point now is to make the contact dynamics having a role in the transmission of the infection, of course. Okay, so how can we characterize the thermalization toward the gamma? Well, there are several ways. For example, you can, for example, just take a BGK operator and then you relax in time toward your gamma distribution. It is, for example, data-oriented, but it's not, I mean, it's a possibility. Otherwise, we can do it, let's say, from a model type perspective. That's what we did. Okay, so we say that the update on the contact dynamics follows this rule. Well, where we essentially we gain. This is a minus here, but phi is negative, so it will be a plus. So we gain contacts up to a certain level that is given by the mean contact of our compartment plus some noise. So we may have some deviation from that. So the noise is centered noise with finite variance, of course. Okay. So the transition function phi is such that we reach mj in several ways depending on the power delta. Essentially, if delta goes to 0, we reach this mj like a Gompers type model. If delta is equal to 1, we reach it in a logistic type way. If delta is equal to -1, we reach it in a von Bertalanffy type with a von Bertalanffy type dynamics. That's not the point. So mj is somehow the threshold that we want to reach. Okay, everybody is going to a given mean plus some deviation from that. So in order to investigate the formation of gamma type distribution, then we have to look to the evolution of our distribution fj, and in weak form, we may set up this very simple kinetic type equation such that the update in the contact type dynamics enters here. And then we may look to large time behavior of this. Okay, it's not easy. So we will see in the next slide that we can prove something. But if we want to show that the asymptotic distribution is a gamma type distribution, well, we have to perform some scaling limit. So our idea is to use a quasi-invariant type limit. So from the Boltzmann type equation that we set up, we pass to a Fokker-Planck type equation that is given here. It's a gamma Fokker-Planck type because it's not really Fokker-Planck. First of all, it takes place in, I mean, the domain is R plus, and then the drift is, I mean, as you see, depends heavily, I mean, in a nonlinear way on V. And also here we have a non-constant diffusion function. Okay, but anyway, formally, we may get the asymptotic formation of a gamma type density for delta that ranges between 0 and 1. Okay, so we are able to describe what we see experimentally under some range of parameters, of course. And if we characterize the asymptotic distribution of our Fokker-Planck equation, then we may compute all the moments of this gamma density that will be finite since gamma has slim tail. So the first order moment is just mj, but the second order moment we see that it can be expressed in terms of mj, of the mean indeed. Okay, so if you don't like this construction anyway, just take, as I said, a BGK type operator, and then it does the job anyway. Okay, we don't see the difference at the macroscopic level, but okay. Okay, at the Boltzmann level, we may prove something actually if we introduce the metric that are the Fourier metrics that has been introduced by Gabetta, Toscani, and Wemberg in 95. That are given by this metric. Indeed, then we may prove that D2 decays exponentially in time, provided this coefficient that depends now on mu and delta is less than 1, but it is indeed in a suitable range of parameters. And then if we have convergence in D2, then we have the convergence of D in DS for S that is equal this less than 2 actually. And then since DS metric is complete for any S that from 1 to 2, then we have the existence of the long time limit fj infinity of the Boltzmann type operator. But the point is that we have no possibility to express it analytically. That's why we use a scaling limit going to the Fokker-Planck equation that has been derived from the Boltzmann type operator that we introduced before. Okay. Okay, at the Fokker-Planck level, anyway, we may prove, again, a lot of stuff like positivity and the contractivity in the L1 norm. These two ingredients makes the Cauchy problem that defines the Fokker-Planck PDE well posed, in the sense that it remains positive for all times if we start with a positive data and integrable data, and uniqueness of the solution under suitable, with a suitable initial data. And okay, so the model that we set up is not a crazy model. It's just, a reasonable model providing you a unique solution and a positive solution under suitable assumptions. Okay, now what the interesting part is that we may determine the macroscopic limit of that, so the observable quantities that can be deduced from our kinetic model. And actually, as I said, if we set our incidence rate that depends on the contact formation dynamics, it can be generalized for any alpha, and it is done actually, but we stick to the case alpha equal to 1 just because it is prototypical. And then we obtain the evolution of mass fractions in this case, and you see that the evolution of mass fraction will depend to a new quantity that is the mean. So a difference with the classical SIR model, now we have a model that depends also on the evolution of mean values of contacts. So we have somehow to close the system. But unfortunately, if we run again we integrate again with respect to x fj, okay, now we have again the evolution of the mean that depends on the evolution of the energy. So we have to close somehow this hierarchy, and how to do that, it depends structurally from the kinetic, the number of moments that we preserve at the kinetic level. Since we preserve mass and momentum, actually we may close the energy taking advantage of the local equilibrium closure. So since the equilibrium of the Fokker-Planck type operator is a gamma distribution, we know this equilibrium closure. So in the range of parameters that provides you the local gamma distribution, then we may close the energy taking advantage of the form of the energy of a gamma distribution. So in this way, we may close the hierarchy, and then we have a system for the contact momentum that is, well posed and depends only on mean values and on mass fractions. So instead of having just 3 equations, we double up the number of equations, okay, because at the kinetic level, we have 2 conserved quantities, that is the mass and momentum, and that's what we get, okay? In this model, you take into account also the evolution of the mean number of contacts under the epidemic dynamics. Okay, but this is a new model. Anyway, this new model, okay, provides you an old one. The old model that we are justifying somehow is the classical case of saturated incidence rate. These are a class of models that have been very well studied in the 70s and 80s. So if we freeze the contact dynamics of the infected, essentially we may close the first order system, solving the equation for MS, so the mean number of contact of the susceptible population. So what we get is this system of 3 equations that you see depends only on the mass fractions. Okay, so all these parameters can be calibrated, taking advantage of data, of course. And for example, in this paper, we try to calibrate the right alpha that appears here, essentially. And for the first wave of the epidemics in Italy and France and Spain, actually, here is the results. You see, of course, there are some deviations since many other social dynamics are taking place in this process. But in any case, you see that we gain some degree of accuracy, taking into account also the evolution of the mean number of contacts. Okay. Once we provided all this framework, so we can justify somehow existing macroscopic models with kinetic models, in a kinetic perspective, thanks to equilibrium closures. So the idea was to determine some optimal way to intervene inside the population, like, I mean, the classical non-pharmaceutical intervention, okay? So the setup of the government, of all the governments, actually, of non-pharmaceutical intervention is an external influence inside the evolution of the epidemics, of course. So that's why we started to study control policies in this setting. So the classical setting is to minimize somehow some cost that depends on the actual number of infectious, okay? So in order to do that, essentially, instead of having a contact dynamics that is given by beta, you reduce in some, let's say, optimal or suboptimal way this contact dynamics, taking advantage of the compartmentalization that you prefer, okay? Can we do somehow the same at the kinetic level? So can we control our kinetic models such that at the macroscopic level, we really see the effect of these constrained dynamics? So in order to do that, there are several problems. So it is the control of kinetic or mean field equation. It is a very well-studied area in recent years. So here there is a bunch of citation in this direction, but it is, of course, partial. And I have to say that, I mean, if we want to find the optimal control policy for a kinetic model, then it is not an easy task. Several people work on that, as I said. And standard solution can be obtained via the Pontriaghi maximum principle. But anyway, for that system, so when the number of particles become large, and we are working already in the limit where the number of particles are infinite or very large, okay, this way becomes unfeasible, okay? So the course of dimensionality plays a real role in this direction. So there are several proposals how to solve this problem, and we will follow the solution coming from the Boltzmann control type approach that we developed together with Michael Herty, Lorenzo Paretsky, and Giacomo Albi for kinetic type equations, okay? So I recall that, I mean, we have this Fokker-Planck model, and what we did before is that for delta that is positive, we have a gamma type density. But interestingly enough, if delta is negative, then we have the emergence of 1 over gamma distribution. It is an inverse gamma distribution. So the question now is, can a central government take some decision without knowing the real contact dynamics of a population? So in certain zones of Italy or of the world, let's say, maybe the contact distribution is gamma, but in other zones, maybe the contact distribution is an inverse gamma. So we have to take some decision to lower the number of infected without knowing really the type of the contact distribution. In order to do that, so we have to take a decision under the uncertainty of the contact formation dynamics, okay? So in order to do that, so we added to the existing model a new one, so a pure control model where we add to the previous type of interaction, so VW prime, it is an interaction that takes place at the same time, okay, on a portion of the agents. So W prime is pure control, and this control is weighted by some function that depends on the number of contacts itself. So for example, if people are, I mean, for people that has a lot of contacts, we may place a control that is very heavy. For people with few number of control, that we can relax a bit the control policy. That's the idea, okay? So what is U now? The U is, I mean, in our proposal, it is maybe not the optimal one, but it is a first proposal that works. And so U is the solution of this minimization problem, such that the post-interaction number of contacts are close to a target number of contacts that are, I mean, the number of contacts that the central government imposed to the population, okay? So it is now VT. And here we have a penalization, okay, such that this functional is convex. So if p is equal to 2, I make the story short, and we may solve it exactly. So the optimal value now is u star that has the scaling that is given here. Okay, so here you see that, I mean, now the kinetic control model takes into account the classical interaction, the interaction represented before, plus a second operator that takes into account only the control part, okay? So essentially, thanks to the introduced scaling, actually, we see that the time of the epidemics is given by 1 over tau, where tau is positive, and the time of the control now evolves with the 1 of the epidemic, because there is no 1 over tau here in front of C. C, the new operator that defines the control, okay? So essentially, if tau goes to 0, what we expect is, even in a control scenario, we relax toward the macroscopic model, and that's what happens actually. You see, I mean, here I will not discuss the numerical part, since we need to implement something that is asymptotic preserving for the introduced kinetic equation. I will not discuss that, but you see that essentially for tau that goes to 0, we relax toward the correct macroscopic model, the one that we derived analytically. Furthermore, the introduced control may have some damping effect at the level of the uncertainty provided by the absence of knowledge of the emerging distribution. Indeed, the emerging mean number of contacts now scales in this way, and then essentially, if we compute the variance with respect to Z, the Z was a parameter switching from gamma to inverse gamma. So if we compute the variance with respect to this parameter, it goes to 0 with the scaling of the penalization of the control. So if we pay, okay, if we don't pay for implementing this control, essentially, we will reduce the variance. And it will be always true for any value of nu, essentially. So what does it mean? Essentially, if here it is reported only the evolution of the compartment rho I and rho R. So we are able to lower the peak of the infection, and at the same time, we are able to reduce the fluctuation around this number. You see here there is a confidence band, and this confidence band is going to 0. So why it is like that? It's like that because in this control policy, we are able to change the nature of the distribution. Indeed, if you select S in a way that is, suitably, smart enough for any value of nu, okay, instead of having a emerging inverse gamma distribution globally, we reach a distribution that has slim tails. Okay, so if we penalize less and less, essentially you see that the displacement with respect to the expected value goes to 0. Okay, so that this is what it means that this confidence band is going to 0 with the penalization. Okay, just few slides and then I stop. Essentially, here the emerging macroscopic model takes into account the control part, of course, and we may apply the same strategy that we have seen before. So we close the system at the second order moment. It is a little bit more complex, of course, since the second order moment now takes into account 2 rather different distributions, but under some assumption on the nature of the uncertainty, we are able to close the system. So at least under some, in some cases, we can provide analytical evidence of what happens. Okay, we also face the problem of confronting what we are doing with real data, but I will not enter too much into detail of that. Okay, now maybe this one I will chat a bit on that, since thanks to our collaboration with Lombardy region in Italy, was possible to see in a model that has also age classes whether what we are doing is sensed or not. In a 1 or 2 week prediction scenario, we compare the real data with the outcomes of the model, as essentially up to 1 week, the outcomes of the model are pretty okay and I mean reliable. Over 2 weeks, it becomes very easy to very difficult, sorry, to trust in what's happening since the process defining the evolution of the contact matrix are very complex anyway. Okay, so what we are working now is to embed indeed in the formation of this beta, so the real transmission, also some opinion formation phenomena that characterizes especially vaccine hesitancy dynamics. So here it is a sentiment analysis provided by my team, where indeed we study the evolution in time of the distribution of, let's say, a sample selected by a team at the University of Pisa. Okay, and the goal now is to enrich the description, taking into account also the effect of opinion formation dynamics on the epidemic side. Okay, so now I make some conclusions. So we have seen how to develop a system of kinetic equation that is consistent with existing models, but it provides you, let's say, a microscopic perspective to the existing models and is capable to justify the transition rates between compartments. Okay, so thanks to our Boltzmann type control approach, we were also able to define control non-pharmaceutical intervention that were sufficiently robust with respect to the uncertainties of the system. And the future works will be with regard, especially the trends to equilibrium in this setting. And there is also another, say, research line that is certainty quantification for kinetic equations. And in particular, we are working on kinetic equation with long-range potentials. And of course, the control in the presence of uncertainties has to be studied more in details, since the control policy that we adopted is somehow simplistic and can be made more rich, of course. Okay, it is a small bibliography on the works that inspired this talk. And okay, last, there is a group of UMI. Okay, if you are interested in let's say collective dynamics, please take a look to the website, and if you want, you can even send me an email to subscribe, let's say, to this group. And in a few weeks there will be this seminar by Ethan Tadmore that we invited. So if you are interested, please take a look to this website. So thank you for the attention.
Thank you, Mattia, for your seminar. Questions from the audience? Okay, maybe I will start with one. So at some point you introduced the parameter delta as an uncertain parameter. And so my curiosity is, probably this is not strictly needed for the analysis you showed, but is there any possibility to ascertain the distribution of this uncertain parameter, maybe from data or something like that?
Well, I'm not very sure about that, since probably what a policymaker may do is to assume, let's say, the worst case scenario, such that let's say a uniform distribution of Z, such that there is no bias in the selection of the contact formation dynamics, and then at that point you have to use some numerical perspective, because at that point you cannot analytically compute the emerging macroscopic model that is emerging, from the kinetic model.
Okay, I think also because the problem is that this delta is, of course, a parameter that you have in the model, which maybe has not a strict physical, meaning it is an exponent at some point of your function. So it may be difficult to relate it to real data.
Well, actually, delta, yes, but of course, the emerging distribution is gamma or inverse gamma. Then, of course, it is a mathematical interpretation of the dynamics. But I mean, the emerging distribution are the two that plays a role. Okay.
Sure. Okay. Questions, remarks, comments?
I know that in France we have the contact, what they call the French connection, the contact of many people. Do you have the same data in Italy, which have been recorded?
It is actually this paper, Béraud and collaborators, is indeed the paper where they developed this contact distribution. Okay, they presented the full contact dynamics. It was in the talk. But I substituted this figure with this one, actually. Well, we are taking it as a reference for the experimental setting. Then, and then, yeah, I mean, we provided some theoretical understanding how to relax to this gamma distribution, since it is not classical distribution indeed. Yeah. And in Italy, we have, I mean, there is a work of Vespignani and collaborators where they try to estimate this contact dynamics. But indeed, the point is that it changes during an epidemic. Okay, it changes. It's not like that. I mean, during an epidemic, as we have seen here. Okay, there is an underlying information dynamics that makes this contact distribution change, and then how can a policymaker take it into account?
Everybody ask himself, what is this small, in the previous slide, why you have this, at 40, there are many people at 40, why?
Since it is experimental, I think it was a bias in the experimental setting, to be honest. Yeah. Because indeed you see that here there are even, I mean, people over 40, so.
And these super spreaders, where are they?
Super spreaders, I mean, super spreaders, I mean, maybe they are normal people, but we high number of copies of virus, I mean, in their blood, in the sense they may infect a lot. Yeah, probably, maybe.
Any more questions? Okay. If not, we thank Mattia again for the seminar.